our first talk doesn't start till 10, so we've got a little bit of time.
Okay.
Yeah. So get comfy and invite to eat and coffee. Yeah.
The program said something about breakfast?
Yes, they're setting it up right now.
Okay,
Yes, yeah, just have to look.
andra sidan har en programmering i sin tid, man har en jobbare. Ja, 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 är lite gøy å komme tilbake. Ja. Ja, det er sant. Det er greit å kunne litt mye greier. Ja, det er.
Okay, I think we can go ahead and get started. So welcome back, everyone. I hope everyone got a good night's sleep and we were able to digest all the knowledge that you gained from yesterday. So we're on day 2 officially, which is great. I do want to let you know a little bit ahead of time, so there will be one minor shift in the schedule. So the Future Communities and Smart Villages, the 2 o'clock session, will actually be longer than an hour. So we actually planned it to be a very interactive session. So I'm letting you know in advance if anyone has to leave early. You've been pre-warned. But I really hope you can stay and join in with us. The 2 that are, actually there will be 3 after that. So Exponential Education will be moved slightly back. After that, we're actually going to have a presentation from Noroff, so you get a little bit more information about this space and the types of programs that they run here, in case you're interested. And then, of course, I'll give you more information about the full program that I also do for Accel.AI in the Bay Area, and then soon we'll be doing here as well. That'll be the last talk, but if you don't get a chance to stay with us for all those talks, that's okay. You can always find more information on our website later on your own time. But yeah, I would like to go ahead and get started.
Did you say it was at 2 o'clock that will be longer?
That's correct.
Yeah, okay.
Yeah. Yes.
When do you think we will end the day?
Yes, so that should only go over by 1 hour. So it'll be an extra hour cast.
So to 5?
Yes. Yeah, 5 o'clock.
Plus?
Yeah. But again, if you can leave whenever you need to. Yeah. Any other questions on that? No? Okay. So we'd like to announce our first speaker. So we have Applying Machine Reasoning and Learning in Real-World Applications with Freddy Lecue from Accenture.
Alright, so hi everyone. So as I mentioned, my name is Freddy. I'm from Accenture Labs. So Accenture Labs is the research and development division of Accenture. It's 200 people globally, and I'm also affiliated with ENSEMBLE, which is a research institute in France. And before joining Accenture, I was part of IBM Research. Work as a research scientist for 5 years on the AI technologies and the AI stack. So the work I'm going to present is some of the work I did back in IBM Research. And now in Accenture we also do a lot of different projects, but I wanted to focus much more on the project we did in the past because of the impact that the work gets on across different cities and different clients we get at that time. So I will really try to explain the business reason of using AI, the technical challenges of applying it, and then how you can provide new solutions for problems that have been here for decades with no real answers. So that's basically the background. So I will go really give kind of concrete examples on how we apply AI. And one of the first problem, well, I spent quite some time when I was working as a researcher in the AI field in IBM is the context of traffic congestion across many different cities. So large cities, because of the number of people and cities and living inside the city, it's growing, and the number of cars is growing as well. You have huge problem of congestions at most of the modern cities right now. And so here just a couple of figures about what is wasted in terms of travel, in terms of gallons of wasted fuel, in terms of how many hours people spending in their cars, whether spending with their families or within the work. So it's all huge numbers. All those numbers are numbers back in 2015, and it's cost 0.7 of the USA GDP. So that's the figures for the USA only, and it's keep increasing. So those numbers, you get stuck in the car, it's keep increasing. Mm-hmm. So one of the problem is first thing is how you build better infrastructures. That's one of the first solutions you can think of. So it's much more on the planning, on the engineering side, but it costs a lot of money. Sometimes it's just not possible. So if you travel to Dublin, you have lots of congestion, and because you have quays and you have a river just crossing the city, there's no way you can expand the streets. There's just no way. So the idea is then how you can basically help the city, any city, to improve the infrastructure, but really not touching the infrastructure, but you by just relying on the data they have and try to understand how we can use the data to better plan and to explain traffic. So one of the things we wanted to do with them is so prediction of traffic delays and traffic congestion I've been studying for years. It's something that even before the AI trends went up, it has already been used and used in the data mining community and the big data community quite a while back, and no really solutions could solve the problem. Or they could find some predictive model by relying on the data, and because of the big explosion of data we have right now, they have better solutions. But prediction is one thing. So prediction is one domain of what AI can be doing in this field of machine learning. So you have huge amount of data about the different patterns, the cars passing by, and basically you try to predict when you will have rush hours, in which locations, and they can build pretty interesting predictive model about what will happen at that time in the city in a given locations. But there is no really way for them for explaining the reason for. So they can say, it's because of weather, it's because of the rush hours, but sometimes you have a random event. It could be some terrorism attack, it could be some large sport events. It could be any random events just has an impact on traffic. And then if it has an impact on traffic, then in real life you have people in a monitoring room that's watching cameras. So basically most of the cities have those cameras that capture different scenes in the city, and they can see what's going wrong, and they can basically try to pinpoint what's the reason. But it's very difficult because they don't have any clue on the reason. It could be an event 2 kilometers away from the traffic congestion because of the propagation effect. It's quite difficult for them to interpret the relational and the connection between them. So we discussed with 4 main cities. So we discussed with Dublin in Ireland, we discussed with Bologna in Italy, Miami in the US, and Brazil and Rio in Brazil, and try to understand how they were solving this problem. And they say, we have good predictive models, but we need to understand the reason why. So because if we know where it's coming from, where the congestion is coming from, why you get this delay, then you can take actions on basically the causes and not on the effect, which is very important in their context. So then how we can explain it? So if I just look up at the existing solutions they have, it's just a screenshot of what the different cities are using. So the one at the bottom is the Torino traffic in Italy. This one is the Dublin one. This one is much more a regional map on the US about the traffic, and they try to mash up data from the traffic data and mash up weather information, road congestions. But if you look at this information, it's nice and colorful pictures about the real-time situations, but there is no insight on what are the correlation effects between the weather, the road traffic, and the colors of the. So the green means it's a the green lines mean that there's no really a problem of traffic. So they really wanted to. They basically use it just for visualizing in real time, but there is no real insight on, oh, there's something wrong here, and it's basically impacting the whole road network, and so it's very difficult for them to interpret. So this is what have been done till probably mid 2010, and they try to analyze data, and they just plot a lot of data on a map, to visualize information, but it was very basic. And again, the same for Torino, they just plot information. And basically, how they get this information, they have infrastructure in the city where, I don't know if you've seen, but on most of the traffic lights, you will have cracks on the road. So you just have very small cracks that nobody can really see it. It's just like if you really watch it, you will see a crack. And you have some captors, and those captors are actually capturing the number of cars passing by. So just by capturing luminosity, they can understand how many cars are passing, and based on the distance between two cars and how many cars they have, then you can start building much interesting models on how the traffic is blocked or congested. And basically this is where you get those colors coming from those cracks that captures the cars passing by. So not really rocket science, but there's a lot of mathematics for understanding how the level of congestion and doing the coloring of the map, but not so much on the AI field, on the machine learning dimension. And here it's a map on the bus. So I don't know if you can really see the colors, but here again you have green lights, red lights, and you have blue bubbles. And those blue bubbles, they are buses. So here's what IBM designed for the Dublin bus company in Dublin. Basically try to monitor those buses and try to see where they are, what's the average speed, how long they've been stuck for, and you have red lights when you have buses which didn't move for quite some time, so that gives this information. But not so much on the explanation and the rationale. And then when you think about the explanation, then you think much more complex systems that need to integrate a lot of data, and that's where you start thinking about AI. And much more advanced machine learning techniques. So as I mentioned, so this is a map of Dublin with the buses on the map, and then you can get the average delay of each and every buses. But the way they use this information, the way they build this system is by analyzing one source of data, which is the bus data. So here they don't analyze the cracks they have on the car or on the road that measure the number of cars passing by. Each and every bus, they have a box, a GPS box, and they basically capture the location of those buses every 20 seconds. So they use a standard, so it's standard used by most of the bus companies, and which capture this information, and then based on this information that they use in real time, and because it's updated every couple of seconds, in this case it was every 20 seconds, you have a streaming of information, and you need to build in real time those kind of graphics. So it was very complex systems to be built, but they were limited in a way that they don't provide any explanation on, okay, I have a red light, I have high delays on this particular segment where I have a lot of buses, and give me the reason for. And the reason for is, well, you can say, well, because you have 5 buses, didn't move for the last 2 minutes, or didn't move more than 100 meters. That could be an explanation, but then you start talking to city managers, they will say, well, that's not an explanation, that there's nothing I can really do on it because you don't really give me the rational, what are the deep explanation. And the deep explanation is maybe those buses are stuck here because there's something crazy going on 2 kilometers away, which basically block the whole road segment, which also impact other roads. And that's where it's starting much more interesting and much more complex in terms of analyzing not only the bus data, but external information. So an external information could be, as I mentioned, weather, events, any source of external information that could impact the road infrastructures, and roadworks is another example of external data. And this platform only used the stream from the buses, so it was very limited in that sense, and so no potential for doing any explanation. It's also called in the AI jargon, it's called diagnosis, so you try basically to pinpoint the reason for something, and no context and no semantics. So no context you basically the data is raw and there's no way of interpreting it. Any questions so far on the yeah?
Traffic lights, is that the cause that you put in the system for congestion?
Well, traffic light is a way for basically controlling the traffic,
Yeah.
but it was not part of the explanation.
Okay.
We
But
didn't.
because roundabouts are supposed to be better.
They are. So they are, but we didn't analyze location of roundabout and location of traffic lights. But basically, the roundabout, you're right, is much better than traffic lights. But still, those two are quite comparable in terms of the impact on the traffic. And what you try to find is not really, oh, you have a traffic congestion because of those particular traffic lights which are very slow, but because actually you have much more cars, and those you have much more cars because of something. So maybe there's an event going on, or maybe they just like a street completely blocked by some roadworks, or you have some kind of weather-related issues in the city, and we try to find external events, not really the infrastructure level, but what's something happening that the city manager doesn't have any control on, and they can have an understanding on.
Okay.
So it's not really on the, we didn't really pinpoint based on the roundabout and the traffic light. Make sense?
Yep.
Any other question, remark? Cool. All right, so what we did is basically try to not only use one stream of data. So the way you can see this thing is you have, it's a stream of information. It's updated on temporal basis. So you just think about the bus information updated every 20 seconds. And you may have at some point, let's say, if it's the purple one, you have the average speed, and at some point it's going up or it's going down, and that just over time. And so you have your source of information. And if you, and it's nice for doing some analytics on top. You can do a lot of things, but the thesis here is let's try to plug in much more source of data. So plug in much more source of data. It could be just the weather, number of events in a given locations, the roadworks, much more like temporal events going on in the city. And then you can add and you can plug them on temporal basis. And the main idea is to find not only correlations across one stream. So let's say this is very high delayed, because this is very high delayed, so there's a connection here. So if you are delayed 5 minutes earlier, then most likely you will have 5 minutes later on. You will try to find a correlation across one source of data with other source. Also, if the weather is not good in some particular part of the country, it may have an impact of some junction of the city. So we try to find those correlations. And this is really where we're coming from the explanation point of view. So how those external source of data might explain those anomalies here. So you can see those guys as anomalies, and basically try to find the correlations and the connections. So that's the very overall approach. So then I'll describe much more details on the data we use. So this is the data. So we have those 4 cities. You have the source of anomalies. So different cities have different challenges. So some really wanted to basically explain why they have delayed of buses, or why they have delay of buses for some, in the context of Dublin and Miami was for the buses, and the context of Bologna and Rio, it was much more on the cracks. We use different sources of information. One used the buses as a buffer to get the anomalies, and the other one you just use those cracks and use much more the traffic flow rather than the bus flow. So it's really depending on who is the client. It's much more the city, it's much more the bus operator. You have different source of information. So some coming from different cities, and they have different information. So you capture different anomalies from different locations, and then you basically try to plug potential explanation. So you don't know what's the explanation. You discuss with the people about, okay, they have a lot of experience in one domain, and you really want to have them give them insight on basically how them as a human pinpoint the problem. And usually the human is very good in getting insight on how they can solve the problem. Because of the nature and the explosion of the data, they just can't do it accurately. And the AI is coming here just to basically find the right insight in the data to get it accurately and as fast as possible. So basically, we just pinpoint and say, okay, what do you think could be an impact, an explanation for bad traffic? And then they end up with a list of things. And so they mention events, mention roadworks, they mention weather information, mention social events, they mention bus passenger loading in the context of bus. So if you have a lot of people in the bus, obviously take much more time for loading people. And it's a lot of things that impact somehow the traffic, some with much more impact than others. And you just list all of them, and let's try to see if we can get the data itself. So when you want to build an AI system, you rely a lot on the data that you have. So if we could only get one of those, you still can build a nice system, but you won't get any accurate results because you have a question?
Yeah, so all those events, those are the planned events. It's not the unplanned accidents or anything. It's only planned events.
So we also have unplanned events.
Okay.
So, yeah,
Okay.
so those ones, they are planned. But the social medias is we get tweets. So sometimes, I mean, particularly in Dublin, the police authority tweet about accidents in real time. So you get this information in real time. It's non-planned, and it's get tweaked to this.
Okay. Yeah.
So it's both unplanned and.
But so, for example, the 285 events in Miami, that would be both planned and unplanned events then, or
So for those ones, they were all planned.
unplanned? Yeah. Okay.
Yeah, those ones are planned
Yeah,
events.
okay.
Those ones are unplanned
Yeah.
events.
Okay.
That's a good question.
Okay.
So, yeah, and then so basically you get these different data. We have a systematic way for accessing the data. So we use existing API. So we have a Twitter firehose for getting access to data. We have the relevant data information we need. Roadworks, we get access to different cities, department where they give us the information, and so on and so forth. So bus passenger data, we have access in real-time data, and social music events. There's existing APIs that give you events, the type, number of attendees expected, what's the durations. So you have a lot of attributes, so a lot of different dimensionality of the description of that particular piece of event. And what the first thing is complex. So the thing I didn't touch, it's so when you build AI systems, 20% is the fun part where you try models and you basically try to change parameters and do various evaluations. 80% is managing this part. You have a lot of data, different format, not aligned in terms of temporal alignment. There's no temporal alignment. You have a lot of noisy data. So 80% is just cleansing, organizing, trying to find out which data to be used. It's just not really the soft fun part. But it's part of the work. So then you have all of these data, and then you have to figure that this one has an impact on your model. So which one is important, which one is not. It's quite a tricky problem, and the AI machine learning community builds some metrics. So you have different ways of evaluating which one is important, which one is not. But as you can see, they have all different formats. You move from PDF, HTML, you have CSV file, you do HTTP call to get JSON description, and it's all messy. You need to reorganize and regroup them in one where you can consume. So, so this one, yeah. But yeah, so this one is just, I think it just adds some pictures and just an overview of what's the different data. So on the left-hand side, you have the eventful. So this is an existing open API that most people can access and give you any events in the major cities. So I'm pretty sure that you have all events in Oslo are provided in eventful. So for most of the cities we tried, they were all available. You have the Wonderground, which also provide open API for getting access to weather and historical weather information. DBpedia is, so you know Wikipedia, right? You heard about Wikipedia? Okay, cool. So DBpedia is the structured version of Wikipedia, and it's basically something you can use for structuring your data. So it's giving you much more relational database style information of the Wikipedia information. And basically, because you have all of this information coming from many different sources, you want basically in the end to reconnect and rejoin these information. The way you rejoin and you build a unique, kind of a unique data set which all connect, you need some glue between it. So you need to so I don't know if you have the Dublin buses, and the Dublin buses is related to some locations, and the weather information you get also another location from a station, so weather stations. You need to reconnect that those locations in my Dublin bus and in my weather station things, they are the same. So one way to do it is just say, well, they are the same. Another way is to say, well, I have an existing dictionary, which is the Wikipedia, and basically make them connected and tell me that actually, this location, it's actually measured in meters. It's actually measured. Yeah.
Why do you use DBpedia and not just a relational database?
So yeah, so the reason if you use relational database, you can join, let's say, locations in bus and location in weather and say they are the same. So it's nice. It could be enough. So why we use DBpedia? Because DBpedia will say, well, location it's actually a distance between location is in GPS units. It could be measured in different ways, and it's a location might be connected to a city or a country and so on. So you have much more context, much more information. So when you build a model, you not only constraints on this only data you have, but you also basically expand the feature dimensionality of your model, because you have information about locations, what's locations, and how they connect to others. So you add much more dimensionality to your problem at the end. So that's the reason why we add this add the glue automatically without you thinking about how you connect things. They give you the glue, and they give you also an extension of this information that you have in your data. Make sense? So that's the DBpedia thing, and then you have the following one is the trips. So it's basically those cracks. So those cracks you see on the there's existing standards for measuring informations, and then you have you have a picture actually of the crack. So here, so that's a traffic light, and here you have some cracks, and you have sensors. So just watch out on some roads, you will see some cracks, and they are very thin, and they measure information. And then you have the buses and the different cameras. So so just to give a bit of context about different cities. So when you say, well, okay, so they try to solve a problem in 4 different cities, it's actually the same problem, and they basically try to create a new system that can be scalable for any city. But the problem is, first, you need to rely on the data, and secondly, so that's the location when you have sensors, those crack sensors you have in the road. So that's the location where you have those sensors, and they might be in different. So in Dublin, you have much less than in Bologna, but in Dublin they capture every 20 seconds. In Bologna they capture the day every minute. So and they use exactly the same standard, but they just use different parameterization. So again, because here you have much less, well, here you have some noise, right? Because here you have maybe two sensors every 300 meters, or maybe 1 kilometer here, and because you have so much noise that you don't have any control in here. And here, well, you have much more control because most of the points are very highly connected and they're pretty close. But because they data every minute, well, it's again, it's not as good as this one because they every 3 minutes. Especially, you have much more density than here because of the time they capturing the data. So you think it's the same problem across different cities, but no, they use different data, and even if they use the same standard, the same information, they just have different ways of capturing this information. So what we end up doing is we start from the bottom to the top, and we just build services. So and those services basically accessing the different data. And they're accessing the different data, and you have different formats. So you have XML, PDF, CSV, WordWorks, tweets, many other type of information. And basically what you want to do is you want to reconcile this information in one format. So we call this simplicity data model, which basically capture the knowledge we get from deploying the systems in 4 different cities, and try to understand which one of those are very important, and then how you connect those things all together. So I won't spend too much time on it because it's quite technical on how you join things. So we have some papers and documentation which is available, which is publicly available. So I'm free to I'm more than yeah.
What's the thing about user data? Contact list and
No, it's a good question. So actually, this architecture is part of a much broader project where we basically try to capture data from the car and data from the user for giving real-time and personalized and customized informations where they were driving. So if you drive to given locations, well, you say I'm going to from A to B, and we know that there's some events between the time you have, and you basically try to understand. Well, because of some time, you need to stop at some point and just to have a break, and because you have a meeting, you have to stop. So just like capturing extra information to based on the traffic to do something. So here it's much more detailed description, but basically because the data is so various and coming from so many different information, you need different way of managing this data. So you use you manage the CSV, which is basically the common separated values data, and then you on top of some tweets, you have a different techniques for extracting the information. On top of the XML, you do something different. On top of PDF, you do something different. And what you want at the end is a very linked and connected thing. So the small things in here, it's what we call a knowledge graph. So I don't know if you heard about that term, but basically a knowledge graph is something where, well, we have different definitions. It's basically, in our context, it's mainly you get data from many different contexts, from different sources. They're all not joined and connected. And you don't really want to build a relational database because you want to build something without a schema. So you join everything, and you end up with a graph with a lot of instances of those data, of the data. So and that's where we will do the reasoning on top. So the title of the talk was machine learning and reasoning. So the reasoning is coming then how you analyze this graph. So you start from very messy data. You restructure everything in one what we call knowledge graph. And you will reason over this graph, and you apply machine learning on top. So you won't only apply machine learning on common and relational database data, but much more on the graph. And in here, probably skip this one, but it's basically give you an idea on what the transformation schema is from one raw data to a much more semantic representation. So here it just actually, it's quite complex, but it only says, well, you have 2 points here. They're all sensors in different locations, and you can capture a duration from moving to here, and there's a distance, and you have a given time, and those guys are the sensors ID. So there's 351 here, there's 44 here, and it's basically kind of very extended description of what those particular connection means, and when you can capture this information, well, you can relate it to some existing nodes in the graph. And here it's how you transform it. So when you get when you get the UID 0, so there's some type, and basically every time it's a CSV file. We only give you 2 IDs, give you the distance and give you the time. And out of this, you just apply this schema, which basically will expand the data, which will make it much bigger, but with similar information, but in a semantic context where you can interpret the meaning of those things, because now you have a meaning of what is this particular idea. You know, it's a sensor in this particular context, and you know that AR1 is actually a word in your particular cities. You have much more what we call semantics. And okay, and here, so to build this graph that connect all the data together, we didn't start from scratch. So it won't make sense to say we have so much data and we just build a kind of a description of all of this in particular information. What you really do is actually you look at what people have been doing in the past on different areas and try to basically to reuse what they have been doing. So in the knowledge graph, or what we call ontologies domain, a lot of people, a lot of standards emerged for describing some domains, could be in financial. It's very popular in the medical domains where body is very complex to understand, and they basically built what they call an ontology, which relates parts of the body, and they explain how those things are connected. And this ontology is very popular in the medical domain. So we didn't use this particular one, but we use other ones that have been developed by the NASA or by the W3C, which is a worldwide consortium for standardizing format, and they also end up with some ontology for modeling time, for modeling geographical information, and we use DBpedia. So just to give you just a very quick overview on, we have a lot of data and we need to join them, and to join them we use existing terminology which have been deployed and developed by other institutions and standard body, because they're very clean, they've been mastered for years, so they're just ready to be used. And we did some extensions. So the C-reverse is the standard for capturing bus locations and the speed of those buses, and there's no really existing domain ontology, so we just built our own, as we just did for the in this case, where we built our own definition of what the description. So here it's a bit more information about the data we have. So it's just to give you some context. So here what you can focus on is mainly on those two columns, on the semantic update. So because we have data coming as raw data, and you have data that is transformed in a knowledge graph or in an ontology, and because they are transformed, you need to understand well how big is the transformation, because you have much more semantics or much more connections. You need to understand how you manage your memory or you manage your storage. And as you can see, you have basically a factor on average of from 5 to 10 from the data you have, and then when you start adding links and connections, basically it's a much more dense information, and it will have an impact on the reasoning and the learning dimensions. Any question on that?
Instead of digging these sensors into the ground all over the city, could you have been using satellite photos instead? Have you looked into that?
Using satellite for capturing what? Capturing the events?
Measuring the cars, how they travel. Could you, if you had a view from above, could you have been following them with the satellite?
Or you mean for capturing patterns of traffic?
Yeah, so you can kind of follow this car from one part of the city to the other by looking.
Well, if you have good resolution, I guess you can do. Even using deep learning for capturing the flow of cars and.
Geospatial?
Sorry?
Geospatial? Geospatial data?
Yeah, kind of if you had a movie stream, film stream from above, like a satellite with the one, say takes a picture every second. Every second, yeah.
Well, I guess you cannot. I don't think people try that. I don't know, it's probably because of the resolution of the data, maybe. I don't know how close you can be to the ground. Is it like, I don't know what's the resolution like.
What if it's cloudy?
Yeah, what if it's cloudy?
Well, you can put them in geostationary orbit, but I mean that would be expensive. You'd have one for each city, I guess.
Yeah.
There are actually several problems with that, because I was related to satellite imaging. So there's first problem is that it's extremely expensive. Second problem is the clouds. Third problem is the vast amount of data, because if you want, let's say you want 2 pixels for a meter, it is already high res, which already, if you let's say have a mid-sized city, it is so much data you can't just put it into the machine learning because it's just so much data. So there are many problems with that. So that's why unfortunately people don't do that.
Okay.
And there is no consensus about when they will do that, because it's just very hard.
Thank you.
A question: how do you handle uncertainty in the input, like a certain sensor type being unreliable, or a certain sensor being
Yeah,
out
so
of sync
yeah.
from a time perspective, or conflicting input for the same object?
So that's when I mentioned 80% of the problem in the machine learning AI community is look at the data and basically cleanse the data. So you need basically to build motions or normal functions to understand is the data nicely shaped, and do you have any noise in the data, and that's part of the problem. You take one and each and every stream of data and basically try to understand, I don't know, conflicting sensors, and basically try to denoise the data and only rely on the one unit. So I don't describe it at all in here, but it's a large portion of the job was to cleanse the data.
But it also could be very varying. I worked on sea surveillance, right? And the weather conditions, for instance, can dramatically impact reliability of a certain sensor, right?
Yeah.
Like a radar or whatever. So it's.
No, you're right. Yeah. No, we haven't tried to correlate the different data except to find how those maybe weather informations of different things impact on the quality of the data. That's really a very dedicated field. But yeah, you're right. You have external factors that impact the quality of the data.
But have you used artificial intelligence for detecting problems in the data?
Well, we do have a group. At that time we do have a group that work on basically trying to understand and work on this particular problem. Our was much more on let's have some kind of okay data to deal with and build some system and see if we can get some good accuracy. And we reached a level where the accuracy was good enough and was validated by the stakeholders and the users. So that's make us comfortable about the quality of the data we managed to get. But we had some metrics to evaluate the quality of the data.
Again, that depends on, I guess, on the goal. Also, if you were to send someone to the moon, you would maybe do even more checking of the data than you did. Because, yeah,
or you can automatically recorrelate, right?
Yeah.
Saying this sensor typically gives 100-meter deviation to the west one, right? So you recorrelate.
Well, in our case, what we did is we have those different sensors, and you basically try to understand the density of those particular sensors, and based on the density, you try to measure. So they measure basically the same thing, and basically you can propagate and get some clusters and see if maybe you have some completely abnormal sensor doesn't really provide data as expected, and that you can start putting weight on some sensors about how they should contribute to the overall network. So we end up with this architecture. So I will spend most of the time now on the on this architecture, so very high level, and try to give you a sense on what we did, and then come back to the evaluations. And I have a kind of a video of the work of the system working, well, one version of it. So this is the architecture. So very high level, it's you get the data. So this is the table I just described, and then out of the data you reconcile the data all together, and you build this graph. And there's a format for capturing knowledge graph. It's called RDF, which basically capture the relationship between entities as a triple. So an entity is connected with, there's a relationship, and this relationship has some. So my name is Freddy. So Freddy has a name. Freddy has a last name Lecue, and there's a relationship. It's a triple. So it's my name, the relationship, and my last name, and it's an example of and everything is connected as a triple, and you end up with many of those triples which built as a graph. And then on top of this graph, you start doing this AI, the AI system. So I describe what's going on in it. But basically, you try to find abnormalities in the graph and try to find patterns that might end up explaining these particular anomalies while describing more details on what it's doing. And then you get the real-time explanations, and you get some accuracy level, and then for each and every location that you are selecting, you have an anomaly, and then basically try to build a kind of a location window on what are the potential impactors. So let's get started. As I mentioned, you have a lot of different data. They all different formats, so you need to reconcile it. You need to basically break the representation format they have, and use only one unique standard for representing it. So we use DBpedia as a glue. So basically, they will connect all of those things, and then you have some existing domain ontology. So the one I had mentioned about the NASA, about the one we define ourselves, and that add an extra glue, an extra layer. And when you have this extra layer, then you can glue those to basically kind of graph with the data you have by remember the mapping schema that we have that transform the raw data to at that level. We have this for each and every data sources, and we will build a big graph. And on top of this graph, you try to do the filtering. So what we do is that's just a subset of a graph. So the graph is basically connecting everything. So it's connecting traffic congestion, weather information, events, passenger loading. I could just connecting everything. And you can see that some graphs are much more connecting than others. So it's just let's say events. So if you have a bus delay in a given street, and you may have one in a month, it's just an exceptional. So you may end up with this particular node here, which is only connected once. And maybe here you have much more connection here, and let's take this one. So here, here it sounds like this guy is much more connected, and it's something about a category comedy, and you have a lot of events about comedy, and many of those events are connected to these particular categories. And basically, what this graph is connected is it's connecting events based on their locations, based on the traffic that you have, and based on the categories of events you have. So you end up with a big graph with a lot of information, and basically it won't give you any explanation, it will just give you some context. So then if you click on a particular location, you can highlight all the events that were happening, and what kind of categories they have, and what was the weather like, and how the traffic was in the overall city. So you can build quite complex queries on top of this graph, and that will give you all of this information. And the beauty of using the knowledge graph or the domain ontologies is you add much more context. So if you only use the relational database and only connect without the ontology, without the knowledge graph, you can only query based on the data that you feed in. Because now I have this DBpedia, I have information about, let's say, Dublin County. So Dublin County has, I think, 24 counties in the Dublin area, and then because it was not in the data itself, but it was part of the DBpedia that give the description of those counties, you can start saying, okay, give me the list of all of traffic congestion on that day, or maybe during summertime in this particular county. And because initially I didn't think about this particular query, but because it's injected automatically by injecting this DBpedia dictionary, which injects a lot of information, you can query on time, anytime, any kind of query which is supported by this DBpedia vocabulary. So which basically help you finding much more correlations, or much more heterogeneous combination of the impact of the context. So rather than just, so if you look at the machine learning field, they end up with data, they try to reduce the dimensionality, the features are predefined, and then if that doesn't work, what they do is they try to add more data, they try to add more features or more attributes, and those attributes they just manually craft it, right? So they try basically to build combination of those and see what those impacts. And here we don't do combination of them, we just add much more dimensionality, and then when you build the model, you can select on demand rather than just recrafting your features and then rebuilding your model and just reevaluating and rerunning it. So that's the main advantage of using the graph. Any question on that?
Is there any reason to use an RDF triple store rather than a property graph for this kind of problem?
So the RDF triple store help you to reason on top. So on top of RDF, you can have existing. So I think I have an example later on. Well, you can. So an example is. So a family event is a social event, And so this is a relationship in the RDF is described as is a relationship. And basically any instance of a family event is an instance of a social event. And that's something you can basically infer using the RDF graph because they embed those properties in it. So you can also add much more complex structures on RDF. So there is an extension of RDF which is called OWL, which is supporting much more expressive representation, and you can build much more complex reasoning system on top. So if you use only a property graph, it will be very limited in terms of the reasoning functionality. The RDF provides much more depth in terms of the reasoning. RDF mainly provides is a relationship, also provides some kind of nice other semantic extension. Any other question? Yeah.
Why do you want to explain this traffic jams? What is the main problem that you're solving?
Oh, so it's coming next. So here we just explain how the graph is structured, and then how we explain traffic congestions. And we will need this graph to understand how we build this explanation. That's coming next. Okay. So I'll move straight away to the example. I think that makes things easier. So you start from the world network. So because the traffic, Dublin traffic is very traffic is propagating over a network, so network is very important in the traffic context. So what you have is you have a traffic congestion in Custom House Key, which is the name of the street in Dublin, and then you have many other streets which connect to this link. And basically, and you have events. Well, the events, this green one might be happening here. You have other events happening here and there, and you have this graph that connects these green events with other events. So it could be a connection about proximity. Spatial proximity or just semantic proximity. So semantic proximity might be this event is about a comedy which happened on a Thursday, and this one is maybe another comedy show happening on Friday. So they are not on the same day, but the same performer is doing the same thing on different days. It's different events, but actually it's very close. It's not close spatially and temporally, but it's close semantically because it's the same style of event. So this is what the graph is capturing. And when you have this graph, what you try to do is you try basically to understand the proximity of events and how these events impacting this one. So that's when we start doing much more interesting things. So what you do is you start simple, it's kind of a Bayesian network style. So you have the list of days, so the left-hand side. So you have your list of events happening any day. You have many events on the day, and you have your list of roads in the segment. And you have an event. You have an event happening at that day, and obviously the event you have right now, it might be a person X performing Y. Maybe is the first time. Is only one time in a lifetime, right? So you won't find this event happening many times. So you try to find is any similar events I've seen in the past that may be close to any congestion at that point. So this is very important. This is very important because, as I mentioned, today you have an event. This is event happening. It didn't happen before, so you don't have any ground truth about how this one only impact your traffic congestion. You have no idea because it didn't happen. So you use these similarity functions, which basically rely on the graph for comparing this event with other any events. And then on that day, on that particular road segment, you try to understand, well, that similar events that I found in the past, does it cause any traffic congestions? And then you try to see, well, there is a traffic congestion. So it was jammed, and it was a free road here. So I found similar events. I didn't find similar events. When I find similar events in here, actually, 2/3 of the case, it was congested. It was jammed, actually. And here 1/3 was a free road. So you can have some estimation about not with the explanation, but it's kind of the correlations between the events and the congestion of the road. And then you can do the same for the no. So you do not find any events, and most of the cases you didn't find any events which are similar to here. Most of the case, well, there is no really traffic congestion. And it's a simple Bayesian relationship between what the probability of the road to be congested given that I see this particular event, and then you can run can reverse those attributes and find the Bayesian probability of this particular event to cause a congestion. So that's only give you for one event, and so the graph is used in these functions. Bayesian, naive Bayesian style is used in here, and what you end up doing is have these events have some kind of probability attached now, because you know that when you have this event, how most likely it cause congestion, and when you don't have it, how most likely it doesn't cause any congestion. So you start having probabilities, and then you do it for each any event which are close, more or less close, much more far away, and then you do it for each and every event. And what you do, then you end up in those events which might be much more far away here. You can start propagating over the graph and closer to here, and try to see, depending on location, so there's some kind of complex functions depending on how roads are connected together and how many events they have, and you start to try to estimate what's the likelihood of those particular two events to actually cause a congestion in here, and then you have this this complex network with some kind of probability of events that probably the likelihood. And because it's a quite it's the temporal effect of an event might be only, I mean, the effect of an event might be an hour, 2 hours, 5 hours, maybe a 5-minute time. You need to play with the time window as well. So when you capture those probabilities, so if I have an event, a traffic congestion now, shall I consider any events in the last 5 minutes, 10 minutes, 60 minutes, depending on the window, the more higher the window is, the more events you add, and the less the smaller will be the probabilities. So you need to play with the windows. So there is some kind of what we call hyperparameters on the model, basically to play with the windows and try to adjust and try to understand, okay, what the best parameters for basically tweaking the models. And again, depending on which events you have, the categories of events, then you start having different hyperparameters for understanding how they do impact it. So does that answer your question about how it's working for the explanation?
Because I still don't understand why you wanted to know the reason of this traffic jams.
Oh, why? Oh, the reason why is the traffic operators, they have a prediction where they will have traffic delays. And they only know when it will happen. They won't know the why. And why they need it is because they need to take actions. So if they know there's most of Thursday, there is always a karaoke event that causes traffic congestion, then they might start rerouting, they might start rethinking about the traffic light strategy. So it's really post-processing. So they know what are the causes of particular congestion, and then they can basically reorganize the overall traffic flow by just forbidden, let's just close some roads on some days, because they know that these kind of events always impact the traffic very badly in those segments. They know what are the causes, and they know where to action on. So that's the main cause for urban planning.
Okay, cool.
Answer your question?
Yes.
Cool.
Okay.
Any question? Yep.
Yes. Is there a reinforcement here as well in that because here you predict?
Yep.
Do you also measure how it actually went?
So we did a validation step. Yeah. We didn't do a reinforcement in the sense that if the machine did something wrong, how we inject it back. So we didn't add this loop, but we did a validation. So basically we build the system, we get the list of results, and we let the user validate the end result by comparing their human judgment against what the system is predicting. And so I get some accuracy results in the end. We didn't do the reinforcement or the interactive learning part. So that's something we haven't built.
Okay, but you can do it.
But it can be done.
Yeah.
It can be done.
You could, for example, connect with Waze or similar apps which are social traffic based and see, because this is constantly 10 minutes too optimistic. So it could need that one.
Yeah.
And I believe it's because it's only based on each person typing in what's wrong exactly now. It doesn't try to predict that it's normally a queue here at 4 o'clock.
Yeah. Yeah, no, you're right. So I don't know how you access the data though, but yeah, that's good. So one thing is, because we as you have seen here, we use the similarity. There's a similarity function here, which basically rely on the graph, and because there is an approximation, based on what has been done, right? So basically, what the user needs to understand is, well, you give me this explanation, and you say that this particular event X is actually this explanation for having this huge impact. But actually, can you give me the real, what's the name, the true element you use in the historical data for basically using as a baseline. So this thing is the thing you see right now. The system thing is the connection and the explanation. But actually, there is no such event in the past in this particular road segment in the past. So it just basically the system approximates using this one. And because it did an approximation based on the similarity in the graph, it may get wrong. So basically, the user wants to say, well, actually, you tell me that this is the explanation because of this event, and your baseline is this event, which is completely different categories. It's maybe the closest one to this one semantically, but it's so far apart that actually I can't really trust the system. So that's when you go back to your reinforcement part, for them to validate the results, they basically use it as a comparison and say, okay, you use all those events. Well, okay, that sounds like quite similar, so that it can give some make sense. All right, so okay, probably have 10 more minutes. So this is the system that's been designed. So I do have a video on it. I'll show. Actually, I have 2 videos. I'll show the other version of it because I have a slide on this one. So very quickly, what you see on the top is Dublin. So you have just the yellow part. So it's the map of Dublin, and the red points are the traffic congestions. The numbers is because the user selected a week or maybe a month time interval, and they get the number of traffic congestions in this particular road. And then when you click on those 36, well, most of the time it's 36 here, they click on this one, they can scroll down and they can see, so here there's a slider from 1 to 36, what the number is, and they can see what the traffic congestion and what it was, and basically what was the severity level. And here you have the explanation part, and the explanation is basically all events which might be an explanation. And just to make sure that we all align, the problem was not only a problem of finding all the closest events to these guys, but finding the explanation. So actually here, if I display all events, which are close to this one, you have many of them in here. And then the system, what it's doing is basically capture those 2 that are the main contributing factors. And this is exactly what this spider chart is doing. It's basically having a multi-dimensional about the type of events, and basically showed two things. It showed the blue triangle and the green triangle, and showed the proportion of events happening in the city, whatever they have or they don't have an impact. And the green ones, the proportion of events that actually explain the traffic congestions. And you see there's a difference, right? So they're all along those 3 dimensions, but events which have roadworks actually, so you have much more. So I think the blue one is the explanation part. The explanation part, and this is the event type. So you have much more roadworks, but actually it's not because you have a roadworks that you have an impact on the traffic. I mean, usually they try to reroute things already. So usually roadworks shouldn't have, they may have an impact on the traffic congestion, but not most of the time because the way it's designed, they do a lot of thinking on it. And so basically, it say that these roadworks actually are not that contributing to the explanations. The road incidents and the social events, actually they are not that big, but they're much more contributing to the overall traffic congestion. So yeah, and then you have the breakdown of all the different categories, and you can see what events happening and the one which explaining, which are different. Explanation? Any clear? So yeah, we just show the context. The user can search across the different anomalies. So there's a video at those different locations. If you want to look at it. So given the time, I'll skip the evaluation part, but we did very deep understanding for the hyperparameters, trying to understand how much historical data you need for building an accurate model, and then depending on what kind of part of DBBT or the graph you inject, how much flexible, how much robust you are, how much scalable you are. So we did quite a few analyses, and then depending cities, you have different size of information, different type of informations, different scalability issues. So it was a very interesting problem because we work across different cities and try to understand on what is impacting work in real time. So so we play with the different DPI parameters and try to define which one is optimal for doing high accuracy and high scalability. So I'll skip this one a given time, but I'll move to the demo part just to give you a sense of what is it doing. So. Okay, so that's Dublin traffic. That's for a 24 hours time window. So it's starting at so you have the time here. Let's see. Okay. So this is the time. And basically what it does is, over a 24 hours window, it just shows events and how they do impact the traffic conditions. So rather than just saying, oh, I have a traffic here congested, what is the explanation? It's the other way around. I have an event here, how it does impact my traffic congestion. And in real time, you see the traffic conditions and how they do impact the different segments of the road. And so I think it started very early in the morning, no only traffic, and then you have rush hours, and then you're starting to be close to noon, and then you will start again rushing hours time. And basically, so sometimes there's no really explanation, they just the rush hours. But sometimes, I think this one was over a weekend, so it was not really obvious reasons. And so Wednesday and Thursday here, it was over a week. And I think I can click on one, and yeah, you have some events, and I just say, okay, from 8 to 12 on this particular day, there's a given tag, and this event actually bring quite a lot of people, and by day historic analysis show that I do impact the traffic conditions. So when the city managers, they do have this information, they know, well, actually, this guy has a huge impact in here. Well, can I do something in it? Can I maybe just change traffic light in here? Can I maybe just reorganize this event somewhere else? If it's a roadwork, can I just stop it every Thursday, because Thursdays always get crazy. So that's one version of the post analysis of the data. So again, traffic, a lot of data coming from many different locations. Those are external events. It's not captured by the traffic authority, and they can be used for explaining it. And they have been used by those city managers and traffic managers and WBS managers to basically have an impact on those events. And they know the explanation, and they don't only know the prediction in real time. They know, okay, what are the contributing factors and the explanations. So this is what we have been working on the explainable AI field, combining machine learning and machine reasoning for solving problem for real world applications. And right now, also working on different type of applications. So working with airline industries for explaining flight delays. Predicting is one issue, but so they want to have some explanation. So what's the rationale? So they know what they can basically action on. So also the idea of actioning what the machine can do. So this is the things we're doing. Also working with in Accenture with our risk office team. Accenture is managing thousands of contracts with many clients. Try to understand which contract might fail, when, and what kind of action you can take to avoid those failures, and give an explanation. Again, the explanation part of the AI. And we're working also in the bank industry, try to detect abnormal transactions, and again, injecting external data, find explanation. That's all the things we're doing in the Accenture labs in Dublin, and basically try to explain why machine learning end up with such a decision. So they build a model, they do a predictions. You can analyze very simple model like random forest, but in most of the cases, you need semantics knowledge graph to be embedded in those models to get the explanation. This is the work we have been doing over the last a couple of years in this context. So, any more questions? I can let the slides open. I think it's planned to get them available. I have videos available of those works. We have publication on those topics at the top AI conferences. Top AI is our Triple AI, Ishkai. So we're traveling to Melbourne in Australia to present some of the work we did on the combination of machine learning and machine reasoning. So I'd be happy to discuss any topic in this field. This is only one application of the work we do. Yeah, go ahead.
Were there any exciting outcomes or insights from this study in Dublin, for instance? Did you figure out that venues are causing all the traffic jams, or anything exciting that came out?
So, well, obviously they reinforce what they already thought about some impact on some events, but sometimes they didn't know that some events have a huge propagation effect, and because the way they structure the data, the city, some particular events they position in some locations at much deeper propagation, much deeper impact, depending on some categories of events. And basically, they basically can use it for basically change the way, the one way or the two ways style of some cities. So they could basically change the infrastructure and do the urban planning. So they learn many different things, but a lot of the main things they learn is that some of the events they didn't know they had a huge impact on the depth of the propagations and also on the wave. They know exactly now which one are they, and then how they can basically try to solve these ones. But some unknown events actually had quite some impact, and they didn't expect that at all.
Yeah, just to touch on that, that means maybe in the wake of a natural disaster, right? An earthquake. So are you able to predict the magnitude and the effect? You get what I mean? The extent of the magnitude.
It's kind of similar in terms of the propagation effect. You can the magnitude is how deep is impacting in terms of the density, and then you have how spread is going. So it's exactly those dimensions. Any other question?
I just Googled, and Dublin should be the world's 10th most congested city. Did you manage to get that lower down on the list, or?
So that's why we address this problem with them, and so we get some recommendations, and the tool have been used for understanding those particular situations. But it don't really solve the problem. They need to take action, right? So it just give them insight for doing some actions, and sometimes it takes some time.
Yeah, of course.
Yeah. Right. Okay. Thank you.
Let's take a 5-minute break. We're gonna have our next speaker plug in. Just get some more water. There's plenty of other food. sure it might take a minute or two for the whole room to get a little warmer again. But thank you. So I'm sure you guys have noticed already that today is a little bit more technical than yesterday. And our next talk will also be a little bit more technical. Okay, wait, no, it's okay. But I want to introduce our next speaker. So we have Emily Barrett talking about AI in law and politics.
Cool. Thank you for that introduction, Laura. So as Laura mentioned, I'm Emily. I am obviously not from here, and that is going to be very important because I'm going to be talking about U.S. law and politics. This is going to be part a sort of theoretical talk and also a very, very applied example. So there will be a GitHub repo that I'll refer to you guys to after this. So who here is aware of what the Supreme Court in the U.S. is? Cool. That's about 50-50. Okay. So this is also very important because when I was about 13, there was a really contentious election, and it came down to the fact that one of the candidates was requesting that there was a recount vote for the national election because it would have meant that he would have won if there was a recount vote. And then it came down to the Supreme Court, which is 9 people who sit on this Supreme Court, that basically were the deciding factor in the fact that this guy was not going to win the election. So it came down to 5-4. So that's 9 people deciding the fate of the U.S. election. That's very important. So I became really interested in law and government, and why is this a thing? Why are 9 people deciding our election? So I became really interested in it a really long time, and so that became really important once I decided that I wanted to be a data scientist. Once I got to the program that I was doing, I decided that I was going to do a project associated with the Supreme Court. I wasn't really sure what I was going to do, but then I kind of was discovering the problem, which is that similar to how when I was a kid, I didn't really understand this court, and I didn't really understand how are these people allowed to kind of decide our fate of our country, basically. So the impact of the Supreme Court is really difficult to handle for the average American. And I really wanted to figure out how to solve this problem. And on top of that, I realized that there were over 36 million words written in the Supreme Court since 1790. If you could think about that, that is, unfortunately, I haven't thought about how many books that would be, but that would be a lot of books of words. It'd be impossible to read all of those cases. And a lot of them are about wheat and things like that, so you don't really want to read them. And then on top of that, the amount of Supreme Court cases that have been brought to the court since that period of time, they've been increasing almost exponentially. That since 1940, there have been 50% of cases. So that's 1790 to 1940, and then 1940 to present is basically 70 years that there has been 50% more cases. So the solution that I came up with when I was thinking about this from a data science perspective was to topic model the Supreme Court cases over time. So who here has done natural language processing? Yeah, that's what I thought. Okay, so that's fine because I'm going to kind of this is going to be the applied version of this talk is going to be the kind of walkthrough about what basically I did and how you can then take my notebooks and do the same project if you'd like to, and you can also apply it to other data. Okay, so now we're going to get into the nitty-gritty of what I did. So I said, I have 23,000 Supreme Court cases. What am I going to do with this? What do you do next? It's really intense thinking about taking that raw data and actually doing something with it. So we're not going to go into this part, but you pre-process, you take out, some punctuation, all that kind of stuff. You'll see that in my notebooks. But so then you need to vectorize. So this is turning your text into numeric values so that you can actually input it into an algorithm. And we'll talk about that. So this is our initial data structure that we're working with. So this is, think about document 1, document 2. These are cases. And the text is going to be just all of the text of every single case in the court. So, and obviously there's more than 2, but that's for example purposes. So what TF-IDF does is it takes the really common words and it downweights them in for putting into the algorithm, and then it upweights the less common words. So we'd see things like the, which is I think the most common word in the English language, I'm pretty sure it is, we'd see the going down, and then judge would be more important. So these would be less common words that are less common across the entire corpus of Supreme Court cases. And then very importantly, each word becomes its own feature in its own column. So this is our new and improved data structure, is that we have Constitution, which is seen one time in the entire corpus, rule is seen a couple of times. So this is, the way that I've highlighted this is so that you can see what words are more important when we're actually going to put them into the algorithm. Cool, so now what do we do? So now we have this, this really big matrix, and that matrix is going to be anywhere from 3,000 to 10,000 columns across. You're not actually going to be able to look at it. So you need to be able to put it into an algorithm that can make some sense of it. So the answer that I came up with for this project was non-negative matrix factorization. So this is maybe going to be a little difficult to explain the absolute math behind this at the moment, but it is, I do go into it a little bit more in my notebooks, so I'm going to try and give you guys the basics right now. So basically, as a rundown of machine learning in general, we want to do an algorithm that's going to describe the relationship between the documents in the entire corpus. So for topic modeling, that would be saying what documents fit into this topic, what documents fit into this topic, and you know, so on and so on. So that is basically a complete understanding of what we're going to do here. So we take that matrix and we basically get to play detective to what the relationships are. So in this particular algorithm, there are two basically secret matrices that we're trying to find the correct product of to then describe the topics. And again, if you have any questions about this, please come up to me afterwards, because I don't want to go into too many details and get you guys muddled down. But so then one of those matrices becomes our topic space. So you know, in a much larger corpus, we'd have D1, D, et cetera, and then there would be topics, so on, and so on. Does that make sense to everybody?
Mm-hmm.
Okay, cool. Okay, so as kind of a rundown of what we did here, we took that 23,000 Supreme Court cases. We extracted, my figure was 5,000 unique values with TF-IDF, the vectorization that we did. And then we clustered into 20 topic groups. So 20 was a number that I selected based on how I saw the algorithm performing. Okay, so one of the really important things that I realized once I actually started doing data science was that communicating is a really important thing. So I couldn't just take these topics and say, okay, I found 20 topics in Supreme Court history and here you go. You know, like that doesn't really work. So one of the things that I was really interested in was trying to figure out how I could visualize this and how I could make it so that any average American would be able to go on with, you know, internet access and basically just say, I want to study the Supreme Court and I would like to know more about it personally, and I want to do it on my own time. So what I came up with was, let me see if I can, your guys' keyboards are different than ours. There we go. Okay. So this is a D3 visualization. So this is slightly different. The GitHub repo will be in Python, and then there actually is the source code to this visualization that I wrote is in JavaScript, which will be also in there, but it's a different language, just so you guys know. So this is the visualization that I came up with. So what I realized was a really interesting story was actually how the topics built over time. And what makes that so interesting is that you begin to see what sorts of social issues are really important in America over, you know, between 1790 and the present. And this would be fascinating with any real, you know, natural language data set that you'd have in Norway or any other European country, I think. And so actually, I'll just click around a little bit so you guys can see some of the things that that I discovered here. Is like, who knows about the civil rights movement in the U.S.? Yeah, figured. So you can see kind of between 1960 and 1990 that civil rights cases suddenly became a lot more important in the consciousness in America, and that makes sense because you have the civil rights movement happening, and you have like all this kind of stuff happening. If you think about it in the concept of that an algorithm took all of these cases and said these are the topics, it's really fascinating thinking about what machine learning has done here. And also just a cool little thing here that you can like zoom in and do that kind of stuff. So just so you know. And this is the link to this visualization will also be on my slides that you guys can see afterwards. And I think I can go back to, does anybody have any questions about the visualization? No? Okay. Cool. Well then, now I'm going to talk about, very briefly, I can't really get into technical details about what I'm doing at work at the moment, but I will talk very briefly about another real-world impact. So this project that I was just talking about, the Supreme Court project, it's more of a toy project. It's kind of for fun, and it's not really going to make any huge impact on the world. But I got the opportunity to join an organization that actually is making a really big impact on the world. And so a big problem in the U.S. is that people can't afford lawyers, and those people end up having to go to a pro bono attorney for either very low cost or free legal advice. And the biggest problem with that is that their intake it really takes up a lot of time. So they have to have a phone call with the person and discuss with them what their case is, and that can take 30 plus minutes per person. So I was approached to do a project where I made it so that somebody could just write in a web form, and then that issue will be classified and sent to the proper attorney all throughout the United States. So there's the current, and there's the future impact or the current impact. And this is it's already live actually, the project that I did. So only 15% of potential clients were even in the pipeline before, and now 100% of potential clients are in the pipeline. And then manual client intake, and now we're saving 2,000 attorney hours, roughly $100,000, and this is grant money, which is really important, saved per law firm per year. And then spending less grant money on administration tasks versus spending more actively helping the client. So this is taking them to the court. This is making sure that they don't lose their houses. Some of these people are writing in that are going to get evicted in 2 days, that kind of thing. So cool. So hopefully I've inspired you now to actually want to do something with data for law and government. And so I've come up with a couple of, I'm not as familiar with the European data sources, just so you know. I just found them because these were all US centric when I gave this presentation last time. So, but the European Union data portal looked actually pretty interesting, as well as the Norwegian statistics one. So, and then also, you can go to data.gov is US-centric, and I also believe that if you run my IPython notebooks that you can get all of the Supreme Court data as well if you'd like. Cool. That's it.
Any questions?
Okay.
How long did it take you to code this data for this beautiful graph?
Yeah, that's a really complicated question, actually, because I did the Supreme Court project as my capstone for a data science immersive. So at the time, I was much more of a beginner coder. So I'd say we worked on this project for, I think, the last 3 weeks of the program. So there was a lot of learning also about, I had to do web scraping to get all of the data. So I had to kind of learn how to do the web scraping properly, and then actually input it. So I'd say if you are an intermediate level coder or higher, it would take probably more than a week to do the project. Yeah. Anyone else? No? You seem like you have something.
Yeah, I think so. After you visualize the data, what kind of questions that data helped you to answer? So
Yeah.
how did you apply this visualize beautifully? I really like it. It's amazing. So what did you do with that after?
Yeah, well, so that is the thing. This is why I call it a toy project, is because I don't actually have any way to apply it to anything. What I did was said, this is a really interesting cultural thing to look at. That what I had discovered was that isn't it fascinating, basically, what's been happening in the U.S. and how people had been researching how, it's like PhDs and things like that, had been researching how the Supreme Court cases kind of go with the times of what's socially important. And I would imagine that we'd be seeing more civil rights. This only goes until 2014. So I'd imagine that we'd be seeing more civil rights cases being brought up this year and 2016 as well. It basically the impact that I was looking for it to have was like, isn't this an interesting self-reflection of what our country has been going through since our inception? And it actually definitely was the case that that people did think it was very interesting, because this project actually, and this is I think when you have a really good data science project, it should have crossover appeal. So there were a lot of people who were data scientists who were really interested in it, but then there were also a lot of people who were average people or lawyers or various things like that thought that it was really interesting as well.
Is it available online for public?
Yeah, of course. Yeah.
Cool. I mean, just like for general public, like for the whole world.
Yes, it is on a website.
Okay, perfect.
How did you come up with these topics? Did you?
Yeah.
do
So.
them yourself?
So that is the.
You have 20 topics, and how did you name them?
Oh, okay. So that is actually a really good question. So, full disclosure, my sister is a constitutional lawyer in the U.S. So I got lucky. Is what the answer to that is. But actually, what you end up with doing a topic modeling algorithm is that you can print out the features, which is remember the columns that I was showing you guys, that those columns will end up showing the most important words to discerning that topic. So you actually do end up with, which actually this is, and it's something that I forgot to mention, is there's topic words. So so these actually, let me come up with a better.
This would be a human interpretation, right?
Yeah. So that part's then a human interpretation. That the output is actually topic number 1, 2, 3, etc. But that if you look at this, and especially this is where domain expertise comes in. You always hear about that with data science. That this is where the domain expertise of knowing the Constitution is really important.
How do you interpret this data? Because the language changes over time as well. So, could you see it in a way that not only the classifications and the words mapping is also because some words are used for different things over time?
Sure. Actually, I get that question every time I present this, and the answer is. TF-IDF does a really fantastic job of actually not kind of controlling for that. Especially considering that law language has been pretty much the same throughout history. There's some words that are used that aren't used as much, and there's more formality used. But the words like defendant and appellate, all of those words, they've been in existence since the court's beginning, basically. So, for this particular project, it didn't really matter. But I think that is an interesting concept for maybe mapping out, say, literature. The difference between Shakespeare versus Hemingway is a lot of different language. And that would be actually a really interesting project doing topic modeling for that. Anybody else? Nope. Okay, well, I'll be here, so if you want to ask me any questions afterwards. Thank you.
Also HDMI. You want to do HDMI or you want to do this one?
Bagging and ensemble methods, in scikit-learn, this one's going to be a little bit more of a code walkthrough, and she'll also be releasing the GitHub later on if you guys want to go through it yourself.
Alright, so this one is quite technical. We're actually going to see how all of this happens, We're going to look underneath the covers. And so the first thing I want you guys to notice is that if you go to my Twitter page, if you go to my Twitter page, I have, if you want it right now, I have pinned this tutorial to my Twitter page, so you can just click on this, and that will take you to, hopefully takes you to GitHub, and there is the entire tutorial, and at your leisure, you can pull it down. You'll have to install Anaconda with the full Python stack, and then follow the instructions, and there you go. Do not do it now, it takes too long. But whenever you're ready, there it goes, there we are. All right, so who am I, and who's this person standing in front of you? Well, my name is Omoju Miller. I am a senior data scientist, machine learning at GitHub. And what I've done over the last 15 to 20 years is around reasoning. Spent like a decade teaching machines how to reason like humans, and then spent like 6 to 8 years teaching humans how to reason about computation. And so I did my undergraduate at University of Memphis in Tennessee, then did my PhD at UC Berkeley. So also I worked at Google in nonprofit investment, where I funded interesting things like Khan Academy, built visualizations of computational ideas so that you can actually see them instead of just listening to words. Nigerian by birth, and I love racing BMWs, especially M3. It's always so much fun. So let's go into this bagging and ensemble models. The language that we're using for all this is Python. Python is a higher order it's a higher order programming language. The thing about Python that is good is that you can use that language for machine learning, as well as building all kinds of different applications. So it's a very good language to learn. It's also a very easy language for beginners to learn because it's somewhat readable, somewhat. So here you will see Python. I'm just importing some libraries that we're going to use. This is about print functions, and this is about the plots that we're going to use. And then we're also using something called NumPy. NumPy is like a scientific stack for Python that helps you do like matrix mathematics, higher order matrix mathematics, and it's very, very fast. So that's that. The thing that powers all of this is something called scikit-learn. And scikit-learn is a machine learning library written in Python. It's simple, it's efficient, it's good for both experts and most especially non-experts. So if you want to get your fingers wet, you can use scikit-learn. It's well-established machine learning algorithms. So most of the machine learning algorithms that a lot of people have mentioned today as well as yesterday, they're implementations in scikit-learn. So you could just use those machine learning algorithms immediately. It has lots of amazing documentation. The documentation is very, very rich. So whatever it is that you're looking for, you should basically go to Google, search scikit-learn random forest. The whole thing drops down. It's very, very easily readable. So it's easy for you to jump into. And there are tons of examples. So if you see something and you don't know how to do it, for example, there's something called isotonic regression. We can click on that. Here's all the code for it. You can basically copy and paste and kind of do trial and error to kind of figure out what's going on. So that's scikit-learn in a nutshell. So data. Here we're making some fake data, right? Scikit-learn, here we have it, sklearn is scikit-learn. There's a package in there called datasets. So we're saying from scikit-learn, the package dataset, import a function called makeblobs. And all makeblobs does is it makes blobs. It's fake data. So we're making a data set with 1,000 samples. So that means that we have 1,000 rows. And then it's a two-dimensional data set, X and Y. And we want to have like 20 centers, like 20 blobs, right? And I've made some labels. The Y-axis are labels. I want them to be hot pink and Dodger blue for like boy, girl. And then so if we run this piece of code right now, the first 5 elements of Y, this is what this is right here. Says, give me the first 5 elements of Y. They correspond to these numbers, 19, 10, 8, 1, and 16. Then the first 5 elements of X, so I mean, this is all of X, it's been concatenated. X is two-dimensional. So the first element, the second element, the first element, the second element, right? And then I changed the labels, this Dodger blue and hot pink. So now when I run that again, you see it's hot pink, hot pink. So for this 4.2 and minus 0.5, the label that we want for that is hot pink, and so on and so forth. So if you run this, you have an idea what it looks like. You've got 1,000 data points, 2 dimensions, and the label is also 1,000 labels. So this is what it actually looks like. This is what it looks like. This should be 20 blobs if you count them. 10 of them are pink, 10 of them are blue. This is what our data looks like. And all we're trying to do with our machine learning algorithm is learn a function that can discriminate this data set. And when I say discriminate, can isolate each of the individual blobs. So we want to find a way to cut all this into like individual blobs. That is basically all we're trying to do. So most of the machine learning algorithms that people have been talking about and the data sets that they've been talking about, no matter how big the dimensions are and no matter how complex they are, at the end of the day, what you're doing is you're trying to learn a function that grows through that data and cuts it up into distinct chunks so that every time you want to do something like prediction, you can say, oh, all these guys belong over here, and so this is the label. In a very simplistic sense, that is what machine learning is. Our brain does exactly the same thing. The function that our brain has learned is just extremely complicated. But as I'm looking at you now, I'm putting all this visual information into my brain. My brain is processing it, and it's learned this function very fast to say, I have discriminated this entire room into saying, all right, human, 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 male human, female human. They're sitting on chairs. Oh, that is a chair. Oh, this is a water. Like everything is basically the same exact thing. We're just doing in a very, 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 maybe this is like the brain of an ant. Very, 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 very simple. So this is what the data looks like. And today what we're going to talk about are tree-based models. So like learning a classifier can be restated as learning a partition of the X and X space, which is this X space here, matching as close as possible to the best partition that systematically predicts for every single X, this is the Y we want. Basically, that's what it is. And so this tree-based classifier, the first one we're going to talk about is something called decision tree. Basically, what it does is just cuts that XY space into orthogonal axes. It just basically puts lines through it and says, this is what I think it is. The reason why this decision tree classifier is interesting to learn, and it's also very simple, is because it's very intuitive. So for example, let's say those pictures I showed you represented like age and gender. So age was like a number, gender, we've coded gender as some kind of number as well. And what we're trying to do is figure out how to cut that data blob based on age and gender. For something like a decision tree, let's say the thing we're trying to ask is, does this person like computer games? So all that data sets there, every single point is a human being, and based on age and gender. So we can say, if the person is less than 15 years old, we're gonna assume yes, they like video games. So we'll go down this direction. If the person is, the gender is male, we'll also make an assumption that yes, they probably like video games. And then we come down to this terminal node. And then there's a prediction score that we believe this, and the score is 2. So if the person is greater than 15, so let's say I am older than 15 years old, we'll go down this way. Say, more than likely they don't like video games. It may be true or it may be false. And then there's a score associated with that. That is what a decision tree pretty much does. And the reason why it's very good, it actually works most of the time. And it's easy for humans to understand how it made its decision. So if we're gonna do this in real life, this is actually wrong. Because the people who actually play the most video games are women over 30. But we're not doing like, shoot 'em bang bang ones. We're doing like our little cutesy stuff on Facebook and planting our trees and doing Scrabble, but they're video games. They're video games. So scikit-learn provides a very simple and unified API. API is something called Application Programmers Interface. So basically an API is the thing that lets you connect to another program. The decision tree I showed you, each of the APIs for scikit-learn has an estimator, which is a function that actually is the learning function. So the estimator here is decision tree classifier. So that's like a function for the learning algorithm itself. Then we can do predictions on that learning algorithm. And then we can transform the data. So we'll do the transform, we'll fit it, and then we'll do the prediction. So our learning algorithm for decision tree, we call it sklearn.tree. So that package, I'm going to import decision tree classifier. That is this line right here. And then each of these models has all kinds of parameters that we can tune. So this one I'm going to say, I want my tree to only go down 6 levels deep. So I'm going to say maximum depth equals 6. And then I'm going to learn the model from my training data. And the way I learn it is by calling a fit function on my classifier. So classifier.fit, I give it all of my training set, which is X, and then I tell it what the label is, which is Y. So if we run this, you get that. This is the output is this decision tree function that has been fitted on the data. All this stuff are all the parameters that you could fit, that you could tune to make your function much more flexible to fit your data. So now we've trained our model. That's literally it, just a few lines of code. And then we want to do our prediction. So for the first 5 data points, the first 5 people in this data set, I want to know if they are boy or girl. And assuming that hot pink is girl and Dodger blue is boy, I do my prediction, and it says, oh, look, the first 2 are girls, the second 2 are, and the rest are boys, the first 3. And then instead of getting the output this way, I could also actually get a predicted probability. So what is the probability that this data point is this label? And by doing that, you can see the probability is 0.16. So that's saying the first column, based on if it's hot pink, we can say this first column, this is probably the boy column, and this is probably the girl column. So stronger, that is a girl, definitely a girl. Oh, we're not quite sure. See, even though it said it was a boy, but look at it, it's like 0.58 and 0.14. So it's kind of like, I can't quite decide. Oh, it's definitely a boy. More than likely a boy. So that's the probabilities. And if you plot this decision tree function, it looks like that. Remember I said the decision tree was just like cutting lines in the data? Like straight lines, orthogonal axis? That's it. Just, I've chopped it up and I've said, now look at this. This is probably that space where I couldn't decide whether I was a boy or a girl, because there are more, it's like, it's hard to cut a line to figure out all the pink and blue in this region right here. But this region is fairly all blue. This one is definitely all pink. This is all blue. Basically, this is what a decision tree will do to your data. And these are your probabilities. So there are many of them that we can't quite separate right here. There are some that we can clearly separate. There are some we can clearly separate. This is a decision tree. Why is this algorithm useful? This algorithm is useful because if you have a lot of training data and your training data has all kinds of different kinds of features, your features are not all like numbers. Your features could be like gender, it could be height, it could be income. Decision trees are robust enough that they can handle different kinds of data. And then also because it's simple enough that a human can actually reason about it. For a lot of people in business, like for example, you're doing decision support as a data scientist for a company, and you have all this data, and you've run it through your model, and you have an output. And then you go tell the CEO, I think we should make this action because this is what the model says. More than likely, your CEO doesn't care about what your model says. Your CEO wants you to like, so explain to me why we should do this. And often if you can say, well, based on the data, we looked at the data and we saw that this category of people, if their income is less than this, we think that they have a higher rate of defaulting on the loan. So therefore, we should not grant them this kind of financial product. It's a lot easier for management to accept that than to say, I don't know, it's a neural network. It gave me a number. That's what it said. And usually that's what happens in most machine learning. Like, if your model is accurate, doesn't even matter. It doesn't really matter. What matters is if there's a human that has to make the final call, the human has to have confidence in the model to make the decision based on the output of the model. So for lots of financial industry in the United States, I know you guys have heard about the 2008, the market crash because of all these complex derivatives. And then when they asked the people, so what's going on? People could not explain. They were just like, complex derivatives, neural networks. I don't know what happened. So since then, there's so many laws in the books that when you have models, especially those kind of models, you have to be able to explain them. And because of that, a lot of people are using things like decision trees, random forest, because they lend themselves to more interpretability. So let's talk about what does it actually mean to have an ensemble model. So this is decision trees, one model. Now, what about you can get much more sophisticated? As you can see, these lines are not good enough because there's so many pink and blue all together. What we want to do with any data set is completely separate each of the individual groups so that they're all homogeneous inside themselves. And a way we can do that is by putting together a ton of decision trees. And when we do that, we call it an ensemble, or we call it bagging. And in a very simple way, this is what it looks like. So here is our data set, assuming this is our data set. And what we do is, from our data set, we sample from the data set. We sample with replacement. So I'm just gonna here's my data set, I'm gonna take a sample out of it. Then I'm gonna take a sample out of it. And for each of those samples, I create individual decision trees. So here I've created 3 decision trees. These are decision trees, the nice little leaves at the end. So these are 3 decision trees. And each of those decision trees says, here's what I think the label is, here's what I think the label is, here's what I think the label is. And then they all come together in a nice selection and then they vote. And somehow we aggregate all their votes together, either through a mean or through majority vote or whatever kind of function we want. And then we say, all of us have voted. 80% of us think that this data point is a boy. 20% of us think that this data point is a girl. We're gonna do majority voting. It's a boy. That's basically what ensemble methods do. And in a nutshell, that's what they do. The difference is that each of them might decide they want to vote differently, or each of them might decide that they want to take a different kind of sample. Some of them, especially random forests, what they do is, instead of, the feature space that we had, my feature space was just 2 features. You could have sometimes up to 200 to 5 million features. And you have to decide, do you want to use all of them? Random forests will randomly select some of those features and create different kind of trees. But the process works so well. So this is what it looks like. An ensemble, now we have 2 separate trees. So for this one, we actually have 3 features: age, gender, and the use of computers data. So we have our previous tree that says, if it's less than 15 and it's a boy, they like video games. Then we have another feature now. So we went back to the people and said, do you use computers every day? That might actually let us know whether you like video games or not. And then if you say yes, use computers, we're gonna say, people that use computers, we think they're more than likely gonna like to play video games. People that don't use computers probably don't like to play video games. And so these are two separate decision trees. And then we aggregate their output to figure out the final decision. So the prediction is the sum of the scores predicted by each of the tree. So to figure out if our male child likes video games, here it's 2, we add it to 0.9 where he belongs over here to, and says, this is the score. 2.9 says, this is almost like a confidence that he's gonna like video games. Like if the older gentleman like grandpa belongs here, he's -1, we add it to here, -9. This is the score that we think that this person may not like video games. And that is an ensemble of trees. And in real life, you can have as many of these things as you want. And in competition environments, the reason why people love these trees is that there is competitive data science for like people who just like to, it's actually kind of fun. You compete, you create complex models, and then you can win money. So many people, especially graduate students who are poor and want to make extra money, decide to monetize their intelligence. Maybe if you win 1 or 2 games a year, that's a very nice, beautiful vacation somewhere. And the trees, for most competitions, over 50 to 60% of competitions are won by using trees because you can get as complex as you want and you can keep stacking and adding and you can go crazy. So here is one kind of an ensemble classifier called a bagging classifier. This bagging classifier pretty much does exactly this. So now let's call it, we're giving it 50 trees. The number of estimators, we're saying give me 50 individual decision trees, and then we're gonna fit it, and then we're gonna plot it. Now look at this. It's no longer lines. Each of those trees has done a way better job. Look specifically right here. This was where it was so modeled, so now we have more reds here, more blues here. So you can clearly see that this is way better than one individual decision tree. And now we've kind of pretty much almost separated the two classes. Very few overlap. There's overlap right here, but it's so little. You've kind of like pretty much pulled the classes apart. You've clearly discriminated your data. Here's another one. This one is called extra trees. This one does something different. It just says, it doesn't give you that predicted probability, it just says he forces you to say you are either a boy or a girl, no probabilities associated. And it still does kind of okay, but it forces that line. And then the one that everybody uses all the time, random forest. All of them with 50 trees, the same thing. So visually now you have an idea of what this learning algorithms do, especially tree-based algorithms. Now moving on, how do we decide which of all these things? There's so many learning algorithms. And in professional setting, how do you decide which one you want to use? How do you decide which one best fits your data? And the way we do that is by doing model evaluation and selection. And so for our model evaluation and selection, there are associated errors with each of our models. So we have our training data that has a certain training error. And so for example here, if we are doing a 0-1 loss error, that means that everything that is correct is on one side, everything that is not correct is on the other side. Now, our model that we did, the last one, random forest, the training error is 0. So basically it has learned the entire data set with no errors. Based on what we know so far, is this good or bad?
Sounds like good. Oversimplifying? Or?
It sounds like good, but in machine learning, good is the enemy of best. We don't want to memorize everything. We want to be able to generalize. Because if it has memorized everything, it has memorized noise. So when it sees a data point it's never seen before, it's just like, I don't know. So you want to have like a little space left so you can generalize. No training error is bad. Your model has overfitted. And so what we want is, the training error is a biased estimate of the generalization error. So all this data set that I've seen is not the real ground truth. It's not the real world, but it's a subsample of the real world. And I want to learn from that so that when I'm in the real world environment, I can generalize. The solution is we want to divide our training data into two separate disjoint groups. And usually we use 70% of our data for training and 30% for testing. And so we'll use the training set for fitting the model, and then we use the test set for evaluation only. And if we do that, then we yield an unbiased estimate of what the real error is going to look like. So over here, we go ahead, and what I'm doing here is, remember our labels were like Dodger blue and hot pink? To just make life easier for everybody, I am going to convert those to numbers. I'm going to encode them. I'm going to say 1 is pink and 0 is blue. So over here, I call something called the label encoder. I fit it, I convert it. So this is what X looks like, numbers. Before I converted it, Y looked like this. Now I've converted it to this. So now everything, training, the label, the features, they're all numbers now. They're all real numbers. And then I go in here and create a train test split. And by default, it does 70% training, 30% testing. I do it, I run it. The training error is no longer 0. It's still very small, but it's not 0. And then the test error is that. So now I actually have a more generalizable model. This is still by no means perfect, but at least it's towards what is better. So training score is often very optimistic of the true performance. It's just like very like eager, like yes, 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 but it's not good. The same data should not be used for training and testing, because if you use the same data for training and testing, you are cheating yourself. You want to make sure that you want to generalize. And so we have metrics that we can use for this. One of the metrics we use automatically for a lot of classification, and that's what we're doing, we're trying to classify into classes. One of the metrics that people use is accuracy. How accurate is my model in classifying the data points into the respected labels? So let's see what our classification is. 90%. So 90% is pretty strong accuracy. But that's not enough. It's just a start. We can do something like precision. So remember, yesterday somebody mentioned precision.
Yeah.
And so what is precision? Precision is about the predicted positives, right? This is the equation for precision. The true positives, the real positives, divided by the sum of the true positives and the false positives. Basically, this is what precision is. Precision is the ability of a classifier not to label as positive an observation that is negative. It measures the purity of the positive predictions. And there are many reasons why you want to use different kind of metrics like precision or recall. There are some things, for example, depending on what the problem is. If, for example, you're doing a machine learning problem on detecting cancerous cells, you want to make sure that your precision is very high. You want to make sure that if there is cancer in this cell, you want to detect it. So you want very, very high precision. You don't want low precision. And so let's see what the precision of our data set is. That's not bad, 96%. It's not bad. Another metrics we can look at is recall, recall is about the real positives, like the things that are truly real. So recall is the ability of the classifier to find all positive examples. If we wanted to be certain to find all positive examples, all of them, we would maximize recall. So I'll pick a model that really maximizes my recall. So and recall is not the only one. So let's see. My recall is 86%. So if I want to maximize that, then I'll go back to my model, all those parameters, then I'll start to tune them. So maybe if I added more layers to my tree, or maybe if I actually added more decision trees, I could get better. And that's the art of machine learning, figuring out how to tune this and tune that and learn new things until you maximize the metric that you're really interested in. Now, The hyperparameters are the things that we tune to find the right model that we want to use. And one of the biggest challenges in machine learning is about model complexity. Remember the very first model that we had 0 training error? That was a model that had overfitted. It had overfitted. And that's very, very high. So that's very bad, sorry. So we want to find this nice medium between underfitting and overfitting. And it's often called the bias and variance trade-off. So over here, you have model complexity. This is a model that is less complex, very, very simple model. And often those kinds of models have very high bias. If you get too complex, you get low bias. And often with low bias comes extremely high variance. So it's this like balancing act. This, you see right here at the lowest point of the error, that's where often you want to stop. And that usually corresponds to this. This is your sweet spot. Yesterday, people mentioned gradient descent. Remember gradient descent, like trying to find the local maxima, global maxima going through this valley. So imagine like there's a ball here, and then there's a gradient, which I think is the second derivative of the thing. So you're just trying to roll slowly, like, oh, we're here. Oh, no, let me see if I can go further down. Oh, okay. Can I still go further down? Yes. Can I go further down? Yes. Can I go further down? Yes. Oh, nice. I'm here. Can I go further down? Oh, no. The error is going up. Oh, this is the global maximum. I'm stopping right there. This is about the best model I can get. That is model complexity. And half of our battle is trying to figure out where this line is so we can just stop. We haven't overfitted. We haven't underfitted. The model is not too complex. The model is not too simple. The model is just right. And so here is an example of doing that thing and actually looking at the curves. So you see right here, this is a random forest that I'm trying to figure out how deep should the depth of my tree be. And as you can see, at the beginning, my error is dropping. This is the training error. This is the test error. So at the beginning, they're both dropping. At some point, I keep adding more layers to my tree. My training error will always keep on dropping. But look at what happened. My test error starts to go up. So where is my sweet spot? My sweet spot is somewhere here, where I have lowered my test error and it hasn't gone down, and it hasn't gone up. And so it says something is off here. Something is off here. Should not be 19. Or maybe if you keep on going, it keeps on dropping. But that's where you figure out the training and test error. These are the kind of validation curves that we study to figure out where we're going to stop. So this is where this tutorial stops right now. So I have shown you today a beginner's viewpoint of ensemble methods in machine learning. We started off with decision trees, simple decision trees, and then we got more complex by adding a bunch of them together, either in things like random forest or extra trees or bagging classifiers. So I'm going to stop right here. Do we have any questions? And all this is on GitHub. Yes?
Thank you very much for a fantastic explanation. Two questions. In the beginning, if you go to the first graphs, just a little bit down. Yeah, this ones. So what do we have on this axis? So on the horizontal?
Basically, all of this is what the data looks like. We're plotting the data.
Yeah, I understand.
Yeah.
I mean, what do we have on the horizontal axis and what do we have on the vertical? Is it how much they like to play video games?
No.
Age?
This is just like a fake data set. And what we're doing is just visualizing the data set in a two-dimensional plane. And that data set could represent anything.
Oh, okay, good. And when you say we have three layers of depths, you mean that we have three variables like
No.
age?
It means that the tree itself, this is one layer, this is another layer. And there could be many variables. This layer could have 10 variables. But we're just saying the complexity of the tree, how deep it goes.
Yeah, so a layer is variable, like age.
A layer is not a variable. A layer can have one or more variables in it. It could have one, it could have two, it could have three.
So
the layer is about tree complexity.
I'm not sure that I understand that. So what would be a layer, for example, in this tree?
Right here, this is the first layer. This first layer happens to correspond to just one feature. Here is the second layer. This second layer has one feature and one terminal node. It can get way much more complex.
Why would we distinguish them in this case?
That's how we're making our decisions. We want to walk down the entire tree to figure out where is the terminal nodes. Sometimes one layer is enough, sometimes two, sometimes three, sometimes four. And if you want to talk about this, I'll be around and we can talk about it some more. Any other questions? Thank you for being a captivating audience.
Okay, everyone, lunch is ready, so we can take a break for that. They did warn me that apparently they might do a test fire alarm, so I'm sorry. You do not have to leave the building, it's just a test, so you'll be fine. We'll also continue doing interviews, so I might pick out a couple of you guys to do recorded interviews for us. If you don't want to do them, it's perfectly fine. Just say no thank you, and we can continue. I think that's all the comments for now, and we'll return in about 10 after. live. How's the temperature? Is it better? Yeah, not as cold? Okay. Are we live? Yeah? Okay, wonderful. Well, welcome back, everyone. I hope lunch was good and everyone's feeling comfortable and ready to start learning again. Yeah? So we're going to start with our next talk. We have David Roverso talking about AI for the energy sector.
Thank you, Laura. So I will talk about first a bit in general about big data and machine learning, and then specifically how we use machine learning in the energy sector at ISMAR Systems. First, a very few words about ISMAR Systems. We are a software company working, developing software for the smart grid. So now the energy sector is going through a big change with a lot of new production from renewables, kind of a distributed production. And we have electric vehicles coming into the grid. We have different type of consumption patterns and so forth. A new kind of data coming into the systems from all the smart meters that are being deployed. So we develop software to analyze all this data and give value to mainly to energy distribution companies. So what we build is a kind of we call it a top system that is based in the cloud. So it's based on the Microsoft Cloud, and it collects data from many existing data sources and external data sources that can be social media or can be weather data and so forth, and collect all this data into one unified platform that makes it easier for the grid companies to extract value from all this data. I said already we use Microsoft Azure, so all our software is kind of based on software as a service. I will not talk much about our systems, but the main system is connected grid that connects data from smart meters and present data and analyze this data to see, for example, congestions of transformer stations and so forth. But we're talking about big data and machine learning. Big data has been in the news for a long time now. The first big news was in 2008 on Nature, the first cover of Nature. So everybody is talking about big data, and one common way of defining big data is through these 4 V's. So we talk about volume is the most obvious. Sorry. Let's go back. So big data, because we have lots of data, but also the speed at which the data is coming at us is very relevant, and the variety of the data. So we have not only data from measurements, we have text data, we have video, we have images, we have unstructured data. And then the 4th V is veracity, so it's very important to have an understanding of the uncertainty in the data that we analyze. But this is kind of a classical definition of big data. One nice quote I found recently is that there are a lot of people that know how to move these large amounts of data around, but not many that know what to do about it. Not to do what with this data. So now literally we can move data at lightning speed. We can store unlimited amounts of data, but we need ways of analyzing this data, and that's where kind of machine learning comes in as a set of tools to kind of find meaning in all this data. Machine learning is kind of exploding. It's coming in the news more and more. People start saying that machine learning is as big a revolution as the internet and personal computers. Google is kind of rebranding itself as a machine learning first company. Machine learning is coming on the front pages of Nature as well. And also, as you might have seen, AI and machine learning is attracting a lot of funding also. Venture capital has gone up from $590 million in 2012 to $5 billion in 2016. But before we go into some examples of machine learning, I would just like to have some fun looking at some big data trivia, looking at what happens in 1 second on the internet. If we start a bit small, we can see that there are about 7,400 tweets every second. Now, recently, many are coming from the White House. There are about 58,000 Google searches starting every second. It might surprise you, but there are more YouTube views that start every second, about 68,000. And then if you go to email, there are 2.5 million emails sent every second. What you see here are black and white dots. The black ones are actually spam. And one of the first applications of machine learning in the 90s was actually to filter spam, so to design filters that understand what is spam and what is not spam. Nice forecast about big data. Somebody say that this is already quite old. By the year 2020, we're going to generate about 1.7 megabytes of data per person per second. Doing some math, that comes to about 11.9 petabytes per second, or 1 zettabyte per day. We heard Amit yesterday, he mentioned 20 or even 40 zettabytes per day. But the idea is that, I mean, we're generating more and more data. But what is a zettabyte? I don't know how many of you have an understanding of what a zettabyte is. So I usually use this analogy. If we say that 1 byte is 1 rice grain, then we can say that 1 kilobyte is 1 cup and 1 megabyte is 8 bytes. 1 gigabyte is 3 container lorries. 1 terabyte is 2 container ships, and we're still far from a zettabyte. A petabyte you can cover Manhattan with rice. With an exabyte you can cover the UK 3 times over with rice. And actually with the zettabyte you can fill the Pacific Ocean with rice. So what we are saying that by 2020 we will fill the Pacific Ocean with the equivalent of rice every day. So that's a lot of data. If we take a couple of practical examples, when we scan or sequence the human genome, we generate about 200 gigabytes of data, and that's about 600 container lorries of rice. So each cell contains 600 lorries of rice. If we look at a more technical example, flight engines, aircraft engines, they generate about 20 terabytes per hour. We have 2 engines usually on a plane, fly 6 hours, 28,000 flights on the air, 365 days a year. It's about 2.5 times the Pacific Ocean every year just with data from aircraft engines. So we go back to the fact that at this moment only a fraction of this data is analyzed, and what we do to analyze data, we use machine learning. So machine learning basically is a subset of AI. It started in the 80s. I started working machine learning in 1990, a couple of years after Robert that I was talking yesterday. Actually, I met Robert the first time in, I think it was 92, 93. Then I met him again yesterday. So as I mentioned, one of the first applications of machine learning was filtering spam. But this conference is about also demystifying AI and deep learning. And deep learning is actually an evolution of machine learning that started just a few years ago. And I will get back to that. But first, some classical examples of machine learning. When we draw our credit card on a terminal, if we have a Visa or a MasterCard or any other credit card, this transaction is in real time analyzed, and a machine learning model estimates the probability that that is a fraud. When we are on social media, machine learning is used to analyze and recognize faces of people. In medicine, machine learning is used a lot now. As you have seen, genomic research generates lots of data, and machine learning is used to find correlations between markers in the genome and how different patients react to different medications or different dosages of medications. Autonomous vehicles use a lot of machine learning. I'll come back to that. And additional systems, for example, use machine learning for forecasting. But if we want to simplify the machine learning process as much as possible, we can boil it down to this. You start with a question that is this transaction a fraud or not? Or where is the face in this image? And then we have lots of data that in a way contain the answer to that question. So a lot of transactions that I know were frauds or were not frauds, or a lot of pictures where I have identified the face. And then machine learning in a way analyzes all this data and comes up with a model that will be able to give an answer to that question when new data comes in. So when I have a new transaction, I will get an estimate of the probability of fraud, and when I get a new picture, I will identify where the face is. So this is very simplified, and this basically is only for supervised learning for the experts in the but I mentioned that we're going through an explosion of machine learning in this last 5-6 years, and there are several factors driving that. Of course, data is the first. We have lots of data. Machine learning uses data, so if we have more data, we can build better models. But there are two technical factors that are very important. The one is deep learning or deep neural networks. I'll come back to that. And the other one is hardware, is the GPU accelerated computing. If we start with neural networks, if we look at our brain, this is a simulation of from EEG scans of the human brain. It's estimated it has 100 billion neurons and 1,000 trillion connections between these neurons. What we do with neural network is try to emulate this kind of architecture. This is an example of a neural network that analyzes handwritten digits. If you remember from yesterday, the NIST database of handwritten digits. This is a neural network that analyzes these pixels, and these neurons are organized in layers, as you can see. And the network tries to identify what kind of handwritten digit has been presented in the input, and that is the output of the network. Now, this is a kind of neural network that we were using about 10 years ago. So it's a kind of a shallow neural network. It has only 3 layers. Now we're using much deeper neural networks with many different layers. So this is just a graphical example of a neural network from NVIDIA. This is an actual deep neural network with over 30 layers of different types, but we will not go into the detail of that. But the idea is that the network can analyze, for example, a picture at different stages. So, for example, the first stage is you identify all the colors and changes in lighting or are different easy features, and the more you go deeper, the more complex features you can find, like eyes and noses and faces at the end and people. This is from the software side. From the hardware side, I was mentioning the GPU accelerated computing. This is GPUs are graphic cards that were developed originally for gaming and for graphic processing, but they fit very well these neural network architectures that are very parallel architectures. So this is a hardware that is very parallel and is able to train these neural networks much more efficiently than a normal CPU. So this is a standard card that we use. It uses 250 watts and runs 11 teraflops. Teraflops means trillions of floating point operations per second. This might not mean anything to you, but if you look back, this was the power of the fastest supercomputer just in 2004, so that's not too far ago, which used 6.4 megawatts of power plus air conditioning, and it was in a building like 65 meters by 50 over 2 stories. But we like to compare also to the human brain, right? So the human brain actually runs at an estimated 1 million teraflops. And what's even more important, it uses only 20 watts of power. So if we want to achieve the same raw power, we will need 91,000 of these cards and use 23 megawatts. Sorry. But this was 6 months ago, and now a couple of weeks ago, or 3 weeks ago, NVIDIA released by the way, this is the power that you need to run 2 of these Eurostar trains with 20 carriages. NVIDIA released a new version of this card that runs 120 teraflops. Uses a little bit more power, but it's kind of 10 times as fast. So we need only 8,300 of these and 2.5 megawatts. So you see how technology is kind of catching up here. And that's it, the kind of the power generated by a kind of mid-size windmill. Now I'll give you some examples of the use of machine learning. Self-driving cars, we heard yesterday about that. And we will start with the classical example of the Google self-driving car that uses a laser scanner on the roof and this scanner generates what is called a point cloud. So all the reflections from this laser scanner. And what you see in this animation is what the car sees in real time. So the car needs to understand, okay, this is a car, this is a bicycle, this is a pedestrian, and so forth. the way to do that, they collect lots of data, driving these cars around. So you have millions of examples of how a pedestrian looks like from such a point cloud, and you can use machine learning to build a model that will recognize the same pattern in real time when the car drives around. Of course, you recognize only things that you train for. So this is the classic funny example when the Google car was driving around, and there was an old lady in a wheelchair chasing a duck in the middle of the road. So the car didn't know what was going on, and just stopped and waited. Other companies like Tesla use mainly vision. So this is the latest version of the Tesla Autopilot that uses 8 cameras around the car and does recognizing everything that is relevant for the car when it's driving around. So cars and traffic signs and cyclists and so forth. We're talking about demystifying AI and deep learning. So we can see that this kind of technology is not reserved for multi-million-dollar companies, but these 3 guys, they used 6 months using only webcams, no kind of fancy radar or nothing special, and they built a system that was, at least in the demonstration, is similar to what the Tesla Autopilot can do. So this is actually technology that everybody can use. And actually it's technology that we have in our pockets. Our smartphone use a lot of that. Already yesterday we've seen a picture of, for example, the Google Translator. And I think I can show you a demo of that. I know that there are at least a couple of people that speak Russian or can read Russian, but not everybody. But if you use the standard Google Translator, you can kind of in real time translate what is. So you get kind of a translated window of the word. It was watching that side. Other applications that we have, like on Instagram, for example, you have these fancy filters that do what is called the style transfer. And here you basically take the content from one picture and the style of another picture and generate a completely new one based on the two. With even some extreme examples like this. So here the idea is that the deep neural network understands what is content and what is style and can kind of bridge the two together. And of course you can do the same with movies. Let's see, yeah. So you can change the style of the movie based on a different style. This I like. And there are many such examples, like this one. It was very recent and it's very impressive, like this one. And of course you can do it also with music. This is from Sony Research in Paris, where they take a known composition and they apply a new style. So this is God Save the Queen in the style of a Bach chorale. So this system, actually, they applied it. Of course, if you do it on a known piece, you understand what is happening. They also applied it to unknown compositions, and experts couldn't say whether that was a Bach composition or was just generated. But enough with the funny examples. A bit about what we do at Ismar Systems. We have a good team of data scientists. Now we are 8 people, most of them with PhDs. We cooperate a lot with Microsoft, both on the machine learning part and on how to implement machine learning up in the cloud, because all our systems are in the cloud. And I will show you just a few examples of what we do. About the cooperation with Microsoft, we are invited in many keynote talks. Actually, the corporate vice president for machine learning and the cloud is actually on the board of Ismar Systems now. And I show this because in this conference in 2015, already built, was when was the first time we were on stage with Microsoft, and that was when Microsoft introduced their machine learning offer in the cloud, and they used this funny app to demonstrate that. This is still running on the web, so you can load a picture and machine learning will recognize all the faces, say whether it's a man or a woman, and the funny thing is that it will estimate the age of the person just based on the picture. So if you dare, you can upload the picture. Now this was just developed for this talk, for this keynote, and what they didn't expect is that after 7 days they had 50 million users of this thing. Just for comparison, it took 75 years for having 50 million telephone users and 3.5 years to get 50 million Facebook users. But since this was kind of developed in the cloud, it could kind of scale automatically. So when they got more traffic, they could allocate more resources, and with less traffic, less resources. So at peak, they could handle 2,000 images per second and run on 1,600 cores. And all of this was done with one developer and with zero downtime. So this was completely unthinkable just a few years ago if you are not using applications in the cloud. So I showed this just because it's a nice example of showing the advantages of having systems up in the cloud. But back to what we do with machine learning at smart systems. At the beginning, we were doing a lot of load prediction, so we'll cover a little bit of that. So time series forecasting. Then we do quite a bit of segmentation and customer profiling. And now lately we have been doing a lot of image processing in our drone project that we will take at the end. So the first application was forecasting the load in the power grid. So if we take an example of one of our first pilot areas is outside of Freddy, is a few islands with about 10,000 smart meters. And if you look at the consumption over several years, you see, of course, you have a higher consumption in the winter and lower in the summer. But there are lots of holiday homes or hitter out of Koala. And all these peaks are the weekends, and this period of higher than normal consumption in the summer is the summer vacation. So this is just to show that there are many factors that you need to take in to make a good prediction model. Yeah, this is just a bit more technical, just shows the correlation between temperature down here and consumption. It's kind of linear, up to about 10, 12 degrees, then it flattens out. This bloom here is actually the weekends and the summer holiday. And I usually make the joke that we are in Norway, so we don't see many days above 20, so we don't see what happens. But if you use the same approach and look at data from the US, of course you see air conditioning that has almost as big effect. Let me see if I can use this. Yeah. Please. Almost as big an effect as heating. So we started doing mainly load predictions at substation level. So basically in the distribution grid you have many substations. Each substation that is like this point here serves about 20, 30 houses. So what we do, we predict the consumption or the expected load for the next 24 hours. And then if we see that the prediction shows a peak that comes close to a limit for that substation, then we can generate what is called the demand response plan and try to kind of control the loads under that substation. So in many areas we have controls of through home automation. So we can, for example, heat the house a little bit before the peak and avoid that the floor heating is switched on actually in that time period where we expect the peak. And then we are doing many more predictions now at different levels, at household level, down at the appliance level, and different kind of aggregations. Another time of time series prediction we do is on production from rooftop solar, for example, which is still not a big problem for energy companies, but they expect that it's going to be in the future when this is more and more widespread. And usually it's very easy to predict production if it is like an overcast day or a sunny day, but when there is a varying weather and clouds coming in and going out, then it can be kind of very synchronized peaks and valleys in different areas, so it's important to be able to predict that. Another kind of prediction that we do is predicting peaks after outages. if like it's a cold winter day in Norway or a warm summer day in Italy, then well, maybe not in Italy, but in the US, we don't have much air conditioning in Italy. But when the power comes back, all the thermostats kick in simultaneously, so you have this much bigger than normal peaks that you want to be able to predict, otherwise the grid might go down right away. So that now this is just based on experience from the operator at the station that knows, okay, it's been cold, it's better if I'm a bit careful in connecting the power grid back, but now they can get more detailed information about how big this peak is expected to be. We also do prediction around EV charging. So we look at loads of EV charging stations and try to predict the peaks for the next few hours. Yeah, I will not go much into detail of that. We look, for example, we are in a big European project. It's called Empower, which is aim is to design a new kind of a local market of electricity and flexibility. Now we have more and more households that are both consumers of electricity and also producers, if they have solar panels, for example. And the idea here is to aggregate many such prosumers, as they're called, in an area, and kind of aggregate the flexibility that is available and kind of offer this flexibility to the local energy company. So here we can predict the expected loads, the expected production, and if there is any kind of storage, and the total flexibility that is available. And this then can be bought and sold. So it's a kind of a local market for flexibility. We work also a little bit in smart cities, not at the level of detail that Freddy talked about earlier today, but here we look, for example, at this was a dashboard that we built for Oslo. It was called Oslo Klimavarometer, where we look at data about traffic, car traffic, traffic of cyclists and pedestrians, and make predictions for the next 24 hours based on weather, for example. Also data from charging stations and data about air quality. So this about time series prediction. Then we work quite a bit on customer segmentation. So basically looking at how can we segment customers based on their consumption profile. To do that, usually you need to do first some kind of dimensionality reduction and then some clustering. I'll explain a little bit about that. It might be a bit technical, but basically if we look back at these handwritten digits and simplify it even more, if you say, okay, each handwritten digit is just an 8 by 8 image of pixels, then we have 64 features that come into our system. So we have 64 dimensions. One thing that you can do is to reduce these dimensions into much smaller space, even 2 dimensions, as it is done here with this technique. You can do this with the PCA, with principal component analysis, or with nonlinear methods like this one. And here, what actually happens using this method is you actually separate the digits already just by doing this dimensionality reduction. So it's much easier than to understand what is a 0, what is a 5, what is a 3 in this other space. And then, of course, you do the clustering to find these groups. There are many different methods. This is the classical one. It's called k-means, where you start with, you say you want to find 4 clusters, and you start with some random points, and then you try to find the optimal position of these centers so that you minimize some kind of cost function. And then at the end you get the clusters that you want. There are many methods available. This is from scikit-learn that was mentioned earlier today. Different methods work well in different type of problems, but you can go and look at the documentation if you're interested. So what we are doing here is trying to find different group of customers that have similar consumption patterns. These are all the 10,000 customers in this pilot area on Valer. And what we see here is the first part is a typical summer weekday and summer weekend, the winter weekday and winter weekend put together. So what we do here is first we do dimensionality reduction, and then we try to build clusters out of this. And we have tools to do that, and we identify different kind of profiles. And then we have tools to drill down on these analyses at different levels to find relevant groups. Just some very obvious and simple groups can be like holiday homes. They have consumption only mostly in the weekends and in the summer, and almost nothing in the winter. There are some consumers that are non-seasonal, others that are very seasonal. And then you have, of course, street lighting that is very predictable. It's up there. Now, the next application of machine learning I want to talk about is in our connected drone project. We'll talk a little bit about that. We start with the movie. Let's see if it runs. Yes.
Current methods of power line inspections are slow, expensive, and dangerous. Connected Drone is replacing manual processes with Azure-powered machine intelligence. Drones are sent out on beyond line-of-sight missions. Data is collected using multiple sensors and streamed to Azure. Vast amounts of data is sent through power line-optimized deep learning algorithms. Connected Drone updates component registries and pinpoints faults and weaknesses in this vital infrastructure. Connected Drone is feeling the pulse of the power grid and keeps the power flowing.
So the idea here is try to improve the inspection process that today is done with helicopters flying low flights over power lines, taking pictures, people climbing poles and people walking along the lines and trying to find problems. If we just look at data from helicopters, usually you get hundreds of thousands of pictures. These are from Hafslund in Oslo. They have several 100,000 pictures, and they have several people that every day they look at these and zoom in and zoom out and try to find any problems that are there. So what we want to do is try to support this process and try to automate it as much as possible. So we want to do it with drones, and we want a system that is able to cover all the process from initiations of the inspection, planning of the drone flight, flying the drone, collecting data and analyzing the data. Yeah, we have many partners. I don't need to go into the detail. We started with 2 grid companies, now we have 12, and we have several technology partners that we work with. So to do that, we use deep learning, trying to recognize everything that is on the power grid and try to identify faults. So what we want to do first is a kind of what's called object recognition. So first we want the drone to be able to understand what is out there, and then the next step would be to identify any problems that are out there. Just some terminology. When we look at an image, classically we say we do image classification. If we say, just say what is the most dominant thing in that image, it could be the shepherd or the human or the sheep. Object localization is actually drawing a box around that thing that you recognize. Object recognition is recognizing many different objects in the same pictures with boxes. Then you have semantic segmentation, that is saying each pixel to which object it belongs. And then instance segmentation is you might have several objects of the same type, and you recognize all of them. And then the last one is key point detection, so identifying, for example, the posture of this man in the picture. If you're interested, one of my colleagues made a very nice what is it called? Infographic. That you can find that link. That look at the history of image recognition and which techniques have been used. So what we do, we have been trying methods both from Microsoft Research, the faster CNN method, We have been using methods from Facebook, the YOLO method, and lately we have been using methods from Google research, the single-shot multi-box detector. These are all different type of deep neural networks that do object recognition. I have some slides of that, but we will not go into that level of detail, so I'll just skip this. But then what we get at the end is a system that is able to recognize, to analyze both still images and video, and recognize most of the things that are there. We had several challenges because the first challenge was that these techniques that have been developed that are available usually work on lower resolution images, usually about, for example, SSD and 500 by 500 pixels. And our images usually are very high resolution, 4K pictures, and the objects that we want to recognize are quite small. So it's not like the sheep and the person in that picture, but they are very small objects. So that becomes a problem when you scale this picture down. It becomes very small, and the small objects they become very difficult to identify. So what we had to do was to devise a method of doing this in several steps. So first we recognize like the whole structure, the whole mast, and then we kind of automatically zoom in and crop the picture and look at higher and higher resolution, and then identify all the small components there. And to illustrate that, we see here first an early version that was not able to recognize things from far away, and the new version that kind of zoom in automatically can already recognize the different components from further away. The other problem that we have is that we have many different components that we want to recognize. So what we are trying to do is kind of similar to what you saw the Tesla autopilot is doing. So recognizing things around the car, we are recognizing things below the drone. But we have a bit more complex problem, because for the Tesla car it's not so important if the car that is passing by is a Volvo or is a Volkswagen, or if the person on the pavement is a man or a woman. But for us it's important if it is one type of insulator or a different type of insulator. So we have many more than those that are in this picture to recognize. For some of them, like this pin insulator, we have many thousands images. For others we have very few. So this is a problem for machine learning, because we need data to train models. So one way around that that we use is to use both 3D modeling, and we actually scan the actual objects, and then we cooperate with some gaming companies and put everything into a game engine, and then we can kind of virtually fly around and take as many additional pictures that we need to build a better model. So for example, on the first models that we had, on a very complex picture like this, we had a problem recognizing all the different components that are out there. With the improved model, then we are able to recognize almost everything that is there. But then, so this is the first part, no? Recognizing the objects. Then we also want to recognize faults and anomalies. So to do that, we have developed what we call the intelligent assistant. Basically, it's a set of intelligent functions. Each one recognizes a different type of problem. This is just an illustration of some problems. Could be like cracks in the poles, or it can be, you might be surprised, but woodpeckers create a lot of damage on wooden poles. Then there might be trees that have fallen on the power lines and so forth. And then we work with our partners and identify, add new intelligent functions to the system. I will show you just a few examples of those. This, for example, a system that recognizes when trees have fallen on the lines. This is just a fake tree that we have put just for testing. But there are also some real cases that they are very interested in finding out. So here we recognize both the power lines, and then we recognize whether there is any kind of obstruction on the power lines that we recognize. And this is just another example of that. This is an example that shows that we recognize different things. The blue box that you see here is like the total structure. Then the orange box is this Roverso structure. Then we have these green boxes are the poles, the wooden poles, and then the insulators of different types. And then what we recognize here is that there is this, on wooden poles usually have these caps on top, either plastic or metal caps, and sometimes they fall off. They put those so that the wood doesn't rot, and sometimes they fall off and they need to replace them, and they want to recognize this problem. So this is another intelligent assistant that we have developed to recognize these as missing top parts, as we call This is just other examples of the same thing. And also we need to recognize the different type of insulators. So for example, here we recognize an insulator with this glass discs that has 2 discs, this has 3, and this is another type of insulator, and so forth. Then we have some funny examples. So we want to recognize the missing top hats, and then we have funny examples like this. Let's see. Come on. It's frozen. Oh, no. What's happening to my PC? My PC is freezing. Marques at one point doesn't answer. Okay. Sorry about that. The pointer doesn't work. Okay, maybe we are back. Yes, we have this fine example where we can recognize that there is a missing top parts on a crystal. But here, I mean, the idea is that you just need to put in some logic that, of course, we recognize the pole, so the top part needs to be on top of the pole, so we can avoid these examples. Another type of fault that we recognize, like cracks. So here we see that we identify cracks in these wooden poles, and there are several examples of that. So there are many different type of anomalies that companies, grid companies, want to recognize. We have a list of about 40, 50 different types that are interested in. Then a few, so all of this is implemented with combination of machine learning and image processing, and all of this is running in the cloud. So we had to build a scalable architecture in the cloud that gives us this advantage that we saw of scalability, so that if we have a lot of images to process, then we can scale up and use more resources. I will not go into the detail of that, but basically we have a system that can scale up. It has a compute pool that can scale automatically. So basically we can scale from 0 to more than 1,000 cores, thousands of cores in less than 15 minutes. We've done tests with up to 1,000 cores using 60 GPU nodes and 500 CPU nodes. We were able to process about 180,000 images per hour, compared to what a human can do is about 50,000 a year. This is also very cost effective because when we don't use the resources, we don't pay for them. And then these intelligent functions can be added very easily, kind of a plug and play. When we develop a new model that recognizes a new type of anomaly, then we can plug it into the system very easily. This just graphically shows a case where we had 330 virtual machines in the system, and the green ones are the ones running and doing some job, and the yellow and blue are the ones that are starting up new tasks. This is just a view of the system, the interface to the user, showing all different type of problems, different type of components identified in the power grid. So we will not go into much detail there. We started working mainly with the image data, so either still images or video, and now we are expanding to look also in infrared and radio noise and more kind of 3D information, either from lasers or from other kind of sensors. So we are developing our own instrument package, and we are actually putting GPU power on the drone, so that we can have some intelligence on board, so not only in the cloud, but also on board. Then lately we have been developing a kind of a mobile operational center, so we have a car with drones inside. You can drive around and control the drones and fly around, so it's fun stuff. Last application of machine learning that I want to talk about is more related to condition monitoring and predictive maintenance. And this is a case that we had in the US with the customer there. which is JEA, is Jacksonville Energy Authority, which is a combined electricity and water utility. They have about 300,000 customers. And they have a problem that if you look only at the water meters, sometimes they start reporting zero consumption, and they don't know whether it's actual zero consumption or whether the meter is broken and needs to be replaced or maintained. So what they do, their policy is they wait 3 months. If after 3 months the meter is still reporting zero, then they send the car and to check. So they have to dig it up and check if the meter is working. They send 7,500 trucks every year, and they found out that 80% of the times there's nothing wrong with the meter, so it's a wasted trip and wasted money. So what we did here, we developed a machine learning model that would look at the history of water consumption at this premise, combined with the history of electricity consumption, and additional information about the age of the meter, which type of meter it is, and so forth, and come up with an estimate of the probability that this is a broken meter. And the tests showed that we were 86.5% accurate in this estimation. So now they get a list every morning showing which are the meters with highest probability of being broken, and they drive only to those. And they have seen that they can save about $2.1 million over 3 years just by avoiding all these trips. And I just want to conclude with the video from them talking about this problem.
eSmart Connected Grid is bringing some value to JEA that we've not had before.
Not only did they have a very rich tool set in the Connected Grid application set, but the approach to how they implement projects, the support that they provide behind that, and then, of course, the fundamental, the essence of who they are as a company and the culture that they express to us.
Every week, JEA generates a list of meters we call zero consumption water meters. And to get on the list, a meter has to have had zero consumption for 3 months in a row. If we could eliminate those wasted truck rolls, we could save a lot of money.
Then they said, can we solve this using data and analytic software from our Connected Grid platform?
In this case, it was a machine learning model through Azure, and it worked really well.
They're very closely tied to Microsoft. We really see eSmart as the real front runner in this particular industry.
And the expertise that eSmart brings as being a world-renowned leader in the analytics space to be able to deliver a new service to our members. And that as this opportunity grows and emerges, that we're going to be able to work together and pursue those opportunities.
Very nice project for us because it was like a very well-defined target with good business objectives. So they want to save money and don't send a truck when there is not needed. They had data, so we could implement this in just a couple of months and give some value directly to the customer. So it's a kind of ideal application of real-world application of machine learning. Yeah, sorry for the technical hiccups, but that's what. Thank you.
How is the legislation in the US? I know that at Valo you're not allowed to have a real house as a summer house, etc. And you can use this system to track if people are there or not. Have anyone asked you that question of the personal data connected to that? No?
No, we couldn't use that kind of data.
No?
And it's not so easily available. We could use data about if there were rental houses, that sometimes often they can be empty, so that was put to the system, but otherwise no more detailed personal information.
No.
Another question? I have a general question. So we've heard about many cases where application of machine learning saved a lot of money to companies. And it feels like that those companies which are not involved in this update, they are going to fail. Is it the case?
Yeah, well, especially in the energy business, a lot of companies are struggling because they have like old business models, and energy space is changing very quickly with new small producers, houses that both produce and consume, and so energy price is going down, and these companies are struggling to keep up. So one way of staying afloat and having a future is to use the data that now they have available to improve both their services and how they maintain the infrastructure, for example, and how they can optimize their operation. So definitely machine learning has, not only machine learning, also other type of analysis of data have definitely value for this company.
How far have you come with using the drones in actually checking the lines, power lines?
We launched the first connected drone product the 1st of June.
Okay.
With a few kind of intelligent assistants. Right now it's mainly used to analyze batch of data, so historical data that they have already. So they have hundreds of thousands of pictures taken from helicopters. So now they can run this through the system and automatically find, for example, all the poles that have a missing top out. So the system is up and running, and we are continuously adding new intelligent functionality. But there is also other type of functionality that is not necessarily intelligent, but could be, like right now, the inspector needs to find the pictures, zoom in and zoom out to find the problems. Now we can, for example, analyze together all the pictures of the same power mast and present to him all the pictures of the same insulator, for example, already zoomed in, so he can very quickly check if there is anything wrong with that and skip and go to the next. So he has a much quicker process to this. So it's more effective. Because it's going to be very hard to replace completely the inspector, because they also look for tiny things that are very difficult to automatically recognize. But we'll try to do as much as possible.
Do you build those drones yourself, or is that something you buy off the shelf?
We do both. We use different type of drones. We cooperate with drone manufacturers. One that was in the list was Robot Aviation, for example, that they build the drones themselves. And especially they build this kind of mini helicopters, and those we use for longer range, because the standard quadcopters or octocopters, they usually fly for 20 minutes, so you can't really inspect 100 kilometers of lines with them. But these other ones, they run on fuel, they can fly for 3.5 hours. So use different drones for different kind of tasks.
Could you go back to the link?
Yes.
With,
the infographic?
And 133 slides.
And very delicate slides.
No wonder the PC was struggling. Now I'm trying to go back too quickly. Maybe if I go out and come back in. Let's see. I'm stress testing this computer.
We'll also be sharing slides. So
Oh,
okay.
Okay.
Yeah.
You can look at the YouTube recording.
Yeah.
Here it is. This one. Yeah. Thank you.
Thank you.
Great, so quick break, and then we're going to move on to our next. The next one's going to be a little bit more interactive, which will be fun. And then we'll everyone, welcome back after a quick break. So we're going to move on to our next session. This one's going to be a little more interactive after you get some basic information about the World Education Foundation. So this is our next speaker, is Marques going to be talking about smart villages.
All right, thank you so much. Happy to be here with all of you today. Looks like a bright, brilliant audience. You guys ready to do some work?
Yes.
All right, I like that enthusiasm. Just a little bit about myself, just to put some things in context of why we're here, why smart villages are important to the WE Foundation, and also how we're going to integrate some of those ideas into the workshop that we're going to be doing today. So the WE Foundation really is commissioned to work between three different nexuses or axes. One is academia, so this is where knowledge is actually built. All right, this is where knowledge is actually consumed, and this is where knowledge ultimately reconfigures itself around just the idea and theory, but also into research papers and things that can be passed on outside of the institution. And then technology, of course, as we've talked about today, as well as yesterday, it is a tool, all right? It's a tool that can actually be used to reorganize information, reorganize data, but then also can be applied in certain ways that can actually assist to actually coming up with a solution or approaching a challenge. And then implementation, that's the actual doing part of things. So we really focus on not only thinking about the theory aspects of what we're doing, also combining it with the technology that's necessary to actually move that challenge to a solvable solution, but also how do we implement with communities around the world in order to create real change and impact. Over my course of time, I've worked in 18 countries, traveled to over 70 countries. My background actually comes from, I was born and raised in California. I'm a SoCal boy from Long Beach. Did my undergrad at UCLA. And then I actually got drafted to the NFL. So I played in the NFL for 5 years, but I needed a pivot. There was something that was in me that I needed to express. Not only that, but I wanted my freedom. I wanted to be intellectually stimulated. I wanted to move across borders. So I started the WE Foundation and ultimately created this platform, which is serving in countries around the world. One of the concepts that really started to fascinate me over the time that I've been doing these projects is how do we culminate and how do we create these new smart villages in order to approach some of the most pressing challenges. And no time in history before this have we been as globally connected. Technology has opened up so many doors to understanding other cultures, actually integrating with other cultures. So now it's time to actually take the theories of what digital aspects can do and really start to see exactly what the real change is in the world. So smart villages. The way that we approach smart villages is looking at it as the digital nervous system of the world, okay? And the way that we came to this was, I actually, about 3 months ago, I was approached by one of my colleagues, and she asked me to apply for Singularity University. And at first, I was, not too enthralled. I was like, okay, that could be something cool. Then I started looking into exactly what Singularity meant and what actually, how it could be applied to some of the stuff that we're doing at the WE Foundation. And when we're talking about exponential technologies, we don't know exactly what the world is going to look like after this this curve. But we do know that it's becoming more connected. We know that spaces that used to be rural are now becoming urbanized. We know that a lot of people are actually moving out of rural areas into urban spaces. So, the dynamics in the ecosystem is starting to change from digital also to analog. So I was old enough to actually know a time before there was Wi-Fi. If you ask any other 15-year-old, they probably have no idea. They probably think that the world actually came with Wi-Fi. But, now that we are here, what are we going to actually do about it? And, approaching Singularity, they asked us to look at climate change. So this is one of the reasons why we're looking at smart villages. And ultimately, Anthropocene. All right, it's a fairly new word in the dynamics of things, but Anthropocene basically looks at the effect that humans are having on ecological systems. All right, and we are definitely having an effect on ecological systems, and it's an effect that technology alone is not going to be able to get us out of. All right, just for some context, humans are causing climate to change 170 times faster than any other natural force. All right, but not only that, all right, Greenland has lost 150 to 200 kilometers of pure ice mass into the oceans since between 2002 and 2006. And why is that? All right, in the last 6 decades, all right, human-driven development, as I just mentioned, ultimately has an effect on Earth systems. And if you look at the exponential curve of technology, it's also affecting how the Earth systems are working as well. So that means there's a direct correlation from us having more, consuming more, having more opportunities to engage with different types of tactile experiences with how we're actually communicating with the Earth. All right, and the experts say, that is a purely a function of industrialized societies. All right, and what comes with industrialized societies? Cities. All right, it's projected that 70% of the population will live in cities by 2050. All right, but it's also saying that the greenhouse gases that are accumulated will rise to about 74% within that same region, within those cities. People are moving to cities for different reasons, whether it be work, whether it be education, whether it be an opportunity, or even just the narrative to think that there's a better life in the city, okay? But that may not always be the case if we could actually harness the things and the tools that we need in order to create the change that's available. So, the world is really about narrative. So what if we change that narrative of saying that everything is in the city, all we need is in the city, to actually looking at it in a more holistic aspect and saying, how about we use technology to reintegrate ourselves back into rural spaces? All right, how do we actually look at how we can approach climate change, climate movement, without just saying, okay, all of our answers are in the city? And one way that we can do that is by looking at the development space, but then also looking at urban planning. So this approach that I'm about to present can actually be utilized in the developing space, whether it be through climate refugees or even just sub-Saharan countries where it's close to the equator, where a lot of the effects of climate change are already starting to be very pertinent. To urban planning, where, for example, in Oslo, you have 100,000 to 200,000 people that want to live in the city, instead of actually piling them on top of each other, looking at rural spaces outside of the city in order to create a decentralized community that can ultimately function just as well as any city in that context. So ultimately, the pitch that I approach Singularity with is a combination of technologies that are already here, that are already available, that we can just utilize and start to gather data from in order to create the change. So I'll just walk you through the idea of the concept. All right, so with cheap and ubiquitous technologies that are already available, you can do it. They say AI is easy, AV is hard. Let's see here. Okay, so with cheap and ubiquitous technologies that are already available, we can actually 3D drone map an area and look at the resources that are on the ground in that area in order to understand what resources are there. Then we can run that information through a machine learning process in order to allocate how livable that area is within that community, getting real-time feedback. And once that's there, we can actually have a suggestion of what different type of sensors we could put in that community, whether it be IoT, whether it be small LoRa sensors that can actually map out and start to gather data, real-time data on the ground in the locations that we have. These are some of the Internet of Things sensors, very cheap, very ubiquitous. They have all different types. And then with cell phones, being so ubiquitous, you can have a real-time user interface with villagers in order to make sure that they have real-time data of what's going on within their community, whether it's around agriculture, whether it's around water, whether it's around transportation. Now you have the capabilities to almost look at the vitals in real time of your community. Just like they're doing biohacking, all right, you can actually see the vitals of what's going on in your body. You can also do that with the community. And one of the supporting technologies that we're going to be using as the backbone to running some of these things is called directed acyclical graphs. Similar to distributed ledgers that are actually running out like blockchain, but this is more in a Poisson flow, all right? So, and then you also don't have to mine, okay, in order to create the blocks, all right, which enables for you to have a free access to transactions. You can do micro transactions, all right, and ultimately it's a distributed ledger that can ultimately have security just as great as, if not greater than, blockchain. And the reason why we're looking at this technology, the blockchain is already at 120 gigabytes per hash, okay? So if you actually were to scale and put everything in the world in a blockchain, it just wouldn't be enough space. Okay, but if we're looking at these acyclical graphs, then ultimately we can start to look at scaling the Internet of Things and having a digital space in an analog world. And I won't go into details on the whole mathematics and the scheme around this, but you can get the white paper at iota.org, all right, which explains all of the mathematics behind this. And ultimately, what this does is that it sends out algorithms to where one of these tips is destined to validate two others. Okay, so it has a weight and it has a value, all right, and that one tip actually is looking to validate two other transactions. So as the transaction flow grows, all right, the system becomes more stable and is allowed to actually make more precise and accurate transactions during that time. And through this, the kind of grander scheme of things is that we're looking to build, all right, almost this digital circular community from a very local area, all right? So when we're talking about small local groups, okay, this could be in the middle of the DR Congo, or it could be in the jungle of Myanmar, wherever that may be, we can actually connect them to a larger organism almost in a fractal type of context, and start to connect information, okay, of what's happening in these smaller villages to what's happening in these larger villages and these larger communities as whole. So now you're getting real-time data, and eventually if we are to map out a good portion of the world, we'd almost know what the consciousness of the world would actually be at any given time. And seeing how the ripple effect of what's happening in Africa actually affects what's going on in China, vice versa, what's happening in the US, of what's going on in South America, so on and so forth. So once you have all of this, this platform actually set up, then it's a lot easier to actually exchange data in a way that it could be effective. And for the development space, that's quite important, because what happens sometimes is that you create a project and then you just try, it works in one place and then you just try to scale it. All right, not taking into account that there's geographical locations, there's cultural differences, there's social, economic differences that all affect how the outcome of that project would be. But if you can share a lot of the knowledge that is going on in different contexts, then you can change and tweak just small variables in that aspect and actually come up with a solution that's relevant to that local problem. So just to give one case, now we're looking at how we're going to utilize this time here in this workshop. One of the cases that we've heard actually from the rest of the day, and as well as yesterday, was agriculture. Okay, so when we're looking at different verticals of what goes into this smart village, agriculture and energy are two of the strongest touch points when it comes to village living. So ultimately, as we've heard, new technologies are going to play a major role in the agriculture space when you introduce artificial intelligence and robotics into that space. So, all of these things will start to play a role, and then a lot of data will be coming out of these spaces. So when we talk about data to be gathered, what type of data should we gather in the agricultural space? We can start off by looking at, can anybody name a couple? Maybe if you were to say, okay, there was an opportunity to look at and come up with a solution for agriculture. What type of data points do you think you would need in order to at least start to frame the picture?
Water supply.
Okay, water supply,
Soil quality.
soil quality.
Sun.
Sorry?
Sun.
Soil, okay, sand.
No,
Sun.
The sun.
Sun, okay,
Sunshine.
sun, yeah.
Temperature.
Temperature, all right.
Yield. Where are you farming? Yeah, yield.
Okay, the yield, so average
And
yield.
the variation over years. You should not do the same every year.
Okay, variation over years.
Air quality.
Air quality, okay.
Or pollution in general.
Any others?
Neighbors.
Okay, neighbors. Can you
Neighbors.
expand on that?
Yeah, in terms of other places that are close, that they can
Okay,
share.
so cross-referencing and triangulating what's going on in places around to see what might work in that area, okay?
Topography.
Topography, okay, very good.
Power
Irrigation systems, how the water flows in different areas.
Power supply.
Power supply, all right, very important, okay? All right, you guys are on it, all right? The bright group here, bright group, I like that. So, so one of them is aggregate rainfall, all right? How often does it rain? Does it rain, all right? In what locations does it rain the most? All right, looking at moisture levels in the soil, all right, which is very important. All right, sun exposure, all right, looking at how many days out of the year, does the sun actually come out? These things are important. Okay, looking at the average growth rate of crops, okay, that's another data point that we could actually look into and tap into. Soil content, also mentioned. All right, the types of crops that actually grow in these areas. All right, so matching crops with soil types, all right, could be very important and very critical for yields that we spoke of. All right, market for taste and timing. All right, so what happens a lot of time in rural areas is that they'll get some type of insight. Farmers will get some type of insight and say, oh yeah, this is gonna be the best crop ever. You guys should, use all your land to buy this one crop. And then by the end of that crop season, all right, there's no more market. So they ended up using a whole cycle of aggregation, okay, to actually service something that was actually not a market. So having real-time data of what the market actually needs can actually help farmers understand what type of crops that they should plant. And then ultimately, like ease of transport is really another data point that we could start to look at when we're looking at the full scope of what needs to be gathered when we're trying to paint a picture around agriculture and what data that we need. So, sorry about that. So, this thing has a mind of its own. Bear with me. Okay, so looking at the data value chain, all right, so for this particular project, the hardware that goes into gathering a lot of these data points can come from satellites, it can come from drones, it can come from cars, it can come from bikes, buoys, offshore, off land. So these are the different hardwares that we can start to look at that can actually supply us with data, all right? And then you have the sensors, you have the physical sensors, you have the chemical indicators. All right, what are they actually picking up? Is it something biological? Is it something optical that we can see? Or is it non-optical, something that we can't see? Okay, these are the sensors that can go into the data of actually tracking data and picking up data. All right, then the raw data, that's when we're getting the data in, when it comes in through the zeros and ones. And it could be in time series, it could be in a raster. So this is scanning the images and what those images are about. Arrays, vectors, seismic, movements, video, acoustic. All right, all of these things can actually be utilized and turned into, or utilized as raw data. And then we have our software analytics. Okay, what type of software can we utilize to start to make sense of these pictures? Okay, we have outlier detections We have modeling, we have the data fusion, bringing data sets together. We have data logistics, how they're flowing together. We have visualizations, enhancements. So all of these things can actually be utilized through software analytics, which you guys are gonna, and probably should be a little bit more familiar with. And then the customer analytics, what is it actually used for? So we can actually start looking at these verticals that we're gonna identify today, whether it's energy, weather, agriculture, transport, insurance, education. All these different verticals can actually be looked at when we have a clear picture of how to utilize our data through this flow. So just for a couple of examples, how do we collect data? So when we're looking at IoT, it could be through city bikes, all right? We have city bikes around Oslo, all right? What if every city bike had some type of sensor on it and, connected to how the traffic was in a certain area, or looked at air quality in a certain area, or if it was raining, could actually monitor how much rainfall has actually come down in certain places in the city. So now you're taking these mobile type of devices that are used for one purpose, actually adding sensors and giving them a whole new life of what they can actually collect during their use. Okay? Smartphones, all right? I think I might be the only person in this room who doesn't have a phone and hasn't had a phone for 5 years, but everybody, but ultimately, smartphones are ubiquitous and a lot of us have them, all right? They can actually be used and are used to gather and collect data, all right? So you can look at the location, the speed of somebody, the internet usage, what are they, browsing on, what are their interests, search queries, communication, who are they communicating with, where are they communicating, all right? And then also practical, old school, qualitative, quantitative data, surveys, all right? Self-reporting, civic engagement, scientific research. So all of these areas you can actually gather data from in order to actually, once again, paint that picture, okay? So what to do with the data? I think that's quite important, and this is what we really want to focus on with this workshop is, all right, once we have our data, what do we do with it, okay? Step one, we have to select our data, okay? And, what is the extent of the data that we have available? In all aspects, we might not have all the data, but we have to really understand what types of data we have and how it's actually already collated or it's not collated. All right, as I mentioned, what data is not available and what data do we wish we had? And then we can start to simulate, okay, if there's a missing piece of data that we don't have in our set. All right, and thirdly, for selecting data, what data don't you need to address the problem? So this is really about sanitizing your data to make sure that the data ultimately is pinpoint on the challenge that you're supposed to fix or to approach. All right, processing data, we have to be able to format the data, all right? The data you selected may not be in the format that's suitable, so now we have to start to look at how do we actually format that data to where it can be readable by a machine learning algorithm. Cleaning data, once again, sanitizing that data, removing, fixing, missing data, things of that nature. All right, and then sampling. All right, so instead of running your whole repository of data that you might have, take small bits of data, run that, see what type of feedback loops you have, and then ultimately you get positive results from a couple of small batches, then you can run it on a larger set, okay? And then thirdly, we're looking at how do we transform data, scaling, all right, what machine learning methods, like data attributes, to have the same scale, so zeros and ones, so making sure that they're a binary type of language that the machine can actually understand is quite important when we're transforming our data and we want to scale it to larger applications. All right, and then the decomposition, all right, there may be features that represent a complex concept that may be more useful to machine learning method when split into constituent parts. So this is really breaking down those constituent parts and seeing exactly what's important for that algorithm or that machine learning program. And then aggregation. Can we aggregate different data models from different data sets, aggregate them in a certain way? So this could be time, hours, aggregate those things into just minutes, all right, to make sure that there might be a easier way for the machine to actually read that particular data. All right, I'm not going to go into detail too much about this, but you know, these are some of the things. So when we're talking about preparing with Python or I don't know why, psychic learning. All right, I keep on saying like psychic, but psychic learning. But ultimately, you know, rescaling the data. So after we want to scale this, we want to have these values that ultimately range between 0 and 1. Okay, so we want to rescale our data to make sure that we can get those ranges. All right, when we standardize the data, we want to make sure that the attributes now have a mean value between 0 and 1. So there's ultimately a standard that the machine can ultimately understand. Then we normalize the data. All right, the rows are normalized to the length of 1. So we, you know, so ultimately we can have, you know, a normal data set that runs through 0 and 1, so we know exactly how long that array is. I don't know, is there something that you may want to add to the normalized data?
Yeah, basically it just helps with optimization and efficiency for depending on which model you're running, right? So all these aspects just help to prepare the data. It's just a way to process it prior to putting it in something like a gradient descent, for example. So it just allows it to run more efficiently.
Yeah, very good, thank you. And then binaries data, all right? So this is data that we're using to transform and put it into a binary threshold, all right? A 0 or a 1. All data above a threshold will have a 0, or all data below or equal to that data will have a 1, okay? So as we get into our workshop, what I'm going to ask us to do is to break up into groups, and each of us are going to have a vertical that we're going to be focused on, okay? And ultimately, I'm thinking about maybe groups of 3 to 4, all right? So we can actually get almost every vertical. And what we want to do during the next 30 minutes of time is to really start to conceptualize what our problem is, why we're actually approaching this problem with the vertical that we're having. And then we want to really look a little bit more granular and see, you know, how to create a smart village solution, you know, given your topic. And then we want to look at even more granular, what problems are you trying to solve? Because I think sometimes when we have data, it's not always about having the most data. It's really about identifying the challenge that's most important that data can solve, okay? And then what kind of data would you collect, all right, as a group pertaining to that particular vertical? And then ultimately, how would you collect that data, okay? How would you collect that data in order to start to, once again, frame this picture of coming up with a solution? Questions? Oh, I did a good job then. Yeah. So what we'll do is we'll break up into groups 2 or 3, and what I'm thinking is we have worksheets here, and maybe as you guys break up to the group, one of the group, say representatives, can come up to me, and then I'll check off which vertical that you guys will be focused on, and then I'll pass out these worksheets, and then you guys can work off of these worksheets. And then what we'll do afterwards is that we'll actually present, okay, our concept. So we don't want to answer these questions just in this format. We want to actually create some visuals, and we want to present and create a narrative no longer than 2 minutes that expresses kind of what you guys agreed upon as a group and what type of data flows are needed, how you guys are going about categorizing the data, how you guys will actually use the data to solve the challenge that you guys were appropriated with. So, yeah.
Everyone stand up.
All right, all right, all right. So what is some of the initial feedback from that process that you guys had just now? Confusion, disruption, group dynamics, idea swapping. What are some of the things that actually happened during that process?
Confusion.
Confusion? Okay.
You summed it up quite well.
Did I? I hit all the pain points, huh? All right. What else? Anything else?
Good ideas usually come later, not in the beginning.
Yeah. Okay. That's a good key takeaway. All right. Anything else?
You know, friendships formed and love.
Yeah. That's good. Right. All right. I like that. All right. You know, one of the reasons why I asked you guys what the process was like, you know, is because there is a connection between humans and technology. All right. I'm really fascinated with cyborg anthropology. And there's this particular person by the name of Karen Barad who talks about new materialism. And she dips into a lot of quantum mechanics, quantum physics. And basically, when you're looking at cyborgs, it's not only about technology being created, but also technology is creating us. Okay? So when we look at how we are relational to technology, it all starts with humans, you know, in small self-organizing or organized groups that come together. They have ideas, all right? They see what tools that they have at their disposal, and they utilize those tools and actually to come up with a solution. And that's what you guys did. You guys started to formulate ideas. You guys are bringing all of your past with you into the groups, and then you guys are combining that knowledge in order to create something that's innovative or creative together. Okay? And on a macro scale, that's basically what we're trying to do. How do we create these talking points or these points of data to where you can start to share not only in your local area, all right, but on a global scale? Okay? And we can use technology as a tool to connect these more local ideas to more of these larger ideas. Okay? So you guys did a great job. I saw a lot of little mice in the head just running around the wheel while you guys were doing this. So to get started, what we'll do is we'll just go down the list. We have 2 in transport, so when we get to transport, we might switch that up. But we'll start off with agriculture. The floor is yours.
Yeah. Should I start? Okay. So we started off with creating a self-sufficient village for a little sect. Then maybe we thought it was a bit off topic, so we went back and we looked at just water because we have a problem with water scarcity in our village. So what we need to do is to minimize the water waste in our food production by reusage and by optimization of the water inflow. So we will look at the water usage today in a given period, be a year maybe, so you get all the seasons. We'll see what is absorbed by our crops and what is waste. And we'll have to look at our water source, our water system, evaporation, moist, and all of those things. And we'll have to collect different kinds of data. So we'll look at a small area analysis maybe, or the whole thing. We'll see what we can do more efficiently. And we'll use the water measuring units on the pipes. We'll use sensors, cameras, drones, and maybe even tractors. We'll look at the soil, analyze the soil, the sun, and the timing on when we water during the day, in the different seasons, and in the different areas of the crops or the land. We'll look at the different growth cycles for the different plants and the crops. When do they need more water? When do they need less water? We'll look at the drainage, the lighting, and based on that, we'll make this little system that controls the water system based on all this real-life data.
Yeah, we ended up with a system that gets data inputs and calculates how much water to give out to the different areas and when, based on the moisture and the weather forecast and time of day, the plant's growth cycle, and all that stuff. And it works
so
insanely good.
Very cool. Any questions? Feedback? Questions, feedback?
So with a lack of technology potentially, how would you collect the data? What methods would you use?
If we do not have the technology?
Yeah, so you're in a very rural area, right? So let's say you don't necessarily have Wi-Fi or computers. You know, what would you use? What other forms would you use?
To collect the data?
Pen and paper. We would look at the water machine pipe to see from day to day how much did it sink, what went through the plant, and what can we assume then went to waste.
And we can also do like small area analytics by taking samples from a small area and see how moist the soil is at different given times, to see if you can like have too much water or if you can change the time of the watering system.
Very cool. All right, round of applause. All right, good job. All right, next one is water.
Probably it's better to start somewhere here because you guys don't see it.
Yeah, so we started our discussion by identifying the problem corresponding to our topic. So that would be lack of water in our surrounding, or lack of drinkable water. And the way we would solve it is to inspect our surrounding of finding alternative ways of gathering water.
Yeah. And the data that we will collect, we will collect data about humidity in this area. The thing we will collect data about.
A little bit louder.
Louder? Yeah. Okay. So we will collect data about landscape to understand where this water can be collected. We will explore what kind of plants we have in this area, because some leaves they probably can collect this water that we can extract from them. We will collect data about the weather. We will collect data about, yes, so this is more related to water. And also we will collect data about people in our village, because bigger families have higher needs in water. So we will need to distribute this water in a fair way. Also we will collect data about infrastructure, about roads, or how we will transport it. And also we will somehow try to estimate how much money we have. How much money we can collect from, I don't know, people in developed countries to develop this small village. And so how we will do it? Next part.
So the data that we would process, we would collect from a multitude of sources. We talked about sensors. It could be sensors, hanging in the tree, collecting data about the the humidity, and but also you could probably use satellite images to look at where water would be collected or found. We could do surveys or observations on the demand for the water. It would be weather reports, maps, and probably online databases and things. But it's so the question we would kind of end up with would be: would it be enough water to be collected, and would it be substantial, or would it be sustainable versus also we talked about what maybe we need to actually extract and get water from outside sources as well.
So we can end up with a solution to import this water. Yes, that's it.
Yeah.
Questions? Feedback? Yeah. Real quick before the claps.
I was thinking also about wastewater. You haven't talked about it.
We didn't cover this topic. This is very important.
Yeah, absolutely.
We will think about it.
We'll bring it into the project.
Any other comments, feedback?
Nice drawings.
Yeah.
Yeah.
I guess one of the things that I would push for is, I guess creating some ideas on how how you would actually collect the data in a very practical way. Like, would it be in rows? Would it be in columns? Would you be willing to say, the level at this, the water is at this level, then we can actually feed it in as a 1 because it's over a threshold, or we can calculate it as a 0, so maybe start thinking about ways that we can collate our data in a way that we can feed it into a machine learning system. Yeah.
Yes.
But great job, good job. Next we have first transport.
First transport?
Yeah.
Yeah.
Because there's two transport groups, but who wants to jump in?
Okay, so in terms of transport, we wanted to solve a lot of things, a lot of problems. But first of all, we wanted to give the person going out of the house the info they need to do the right choice in terms of what transportation they should use. What we're trying to solve, traffic jam, time, there's 30% of cars in
30% of all the traffic in big cities are people cruising around for available parking spot.
which obviously costs the society a lot of time, and they should be more productive in this time. Also reduce stress of finding parking lots, and also pollution and the environment and everything. So what kind of data? I mean, the stuff that is affecting this, whether to do either private, go with your own car, or use public transport. So it could be traffic, weather, the cost of this, how much time it takes, and how much pollution you will cause to the society. That could also be something could be interesting. So obviously we want people to take more public transport, and the end answer to this also could be that they could end up booking a parking spot.
We were thinking that by having cameras at the corners of the street and perhaps on the buses that commute, we will be able to map where the parking spots are and when they are available. So from the app we will provide you, you can see, okay, there's 5 available parking spots in the street around the corner, and there's a high circulation of cars there, so they are likely to be available when I arrive.
There's 10 free spots in a parking house next door, and I can book one. And I can book it from within, I'll be there in half an hour. And the public transport is also, I'm gonna go from London to Manchester, but you should be aware of when you're going home, it's gonna be rain and you have to walk 5 kilometers from that bus to your house. So all of these things taking into consideration would make the perfect app.
Yeah.
No? Yeah, of course.
Questions? Feedback?
And yeah, of course, there's a piece of cake of picking up all the data and the info that we need.
Oh, there's cake involved.
Yeah, no questions.
No questions?
I have more comment. I believe actually Oslo Kommune is already putting sensors in some places and doing part of this job.
Yeah.
Mm.
Yeah, so I think a lot of the information that we need is already available. It's just using it in the right way.
Taking away all the
Yeah,
parking spots?
yeah. Someone inside the...
All right, round of applause.
Yeah.
All right, next up is energy. We'll come back to transport so we don't get oversaturated with transport.
Basically, we decided that we were looking at how to solve a problem of energy, and we focused on electricity. That means basically for the house, for home use. And this is then in a place where you probably don't have electricity today. So what kind of uses would you? It would be for heating or cooling homes, and it would be for cooking and for food storage and things like that, for basic usage of electricity. And yeah.
Okay. We went for renewable energy to create the electricity, like the sun power we have, the wind power, and the hydropower, depending on the environment. Also, if it's a cold environment, you want a closed house, you could use heat pumps. And if it's like a warm environment, you could use convection, and you could think of the have the wind blow through the house and think of the architecture. Yeah, so you can do what you continue.
So we looked at a number of things that we could collect in terms of data, but I think one of the key things that we thought about is that the needs of different communities are quite different. So to be able to profile and group similar communities together would be quite useful, and you could use that to look at what they prioritise as being important in terms of energy generation and particular techniques you want to use to generate that power. But I guess we have many different things we could look at, which we have people surveys, so within communities, or if there's government data available to use that. One thing we want to get from part of the survey work for government data is the energy use that they would like to have and what they're using now. We'd also look at the livelihood of people, also general profiles of the population in terms of age, population density, what kind of work they're doing, etc. We'd also get energy peaks of energy need and requirement, and natural disaster. I don't know why we've got natural disasters there, but and also general meteorology data from the local communities. So that was our data collection. I think our overall idea, or something I thought we could do to when you build up this data set, you can create a profile of a community and maybe look at a particular mode of energy generation and apply that in a new community or setting. So you could potentially look at using predictive modelling to see how a particular form of generation might work in that new setting. So that's the general idea.
Very good. Questions, feedback? All right, you guys did a brilliant job. Good job. All right, we'll go right into currency. Show me the money.
And we are saving the environment, so we don't use this one.
Right. So we took here the problem of what if there's a village that is extremely low tech and has not actually implemented the currency technology at all to begin with. And so that will create an issue with the creation of wealth and the retention of wealth. And so in order to increase the method of creating more value in a village would be to find some way to actually implement a new kind of currency to begin with, and also how to make a rural production base more efficient. So the main aspect of increasing the efficiency would be to perhaps create some kind of centralized system for market analysis, so that if you're going to sell, say, a goat or something, then you would have some way of collecting market prices from the different regions around, and collecting them into when you should probably sell at the best time. And additionally, you would have reporting yourself through pretty basic means. You basically just need a phone to enter data into this system, so that the system knows how much availability of resources that you have in your village. And in addition, we would like to increase our security and the ability to accountability and the ability to retain value with blockchain.
Absolutely. Now, just to finish up, I guess Marques talked a little bit about blockchain, right? If you are attentive. Right now, in a world where emergency connectivity and community engagement is assisted by mobile connectivity, digital currency is actually important in this case. And hereby, maybe for the villagers, they can use P2P payments, Pico payments. Have you heard of that? Here, it's pretty much tiny payments, whereby they can use they can create accounts, small accounts also, to like save their money, and basically it can be more. They can assure themselves of how to save their money, or just to be more independent in themselves. So basically, introduction of using the Bitcoin technology, since we're talking about currency, would be a more transparent way and safety of using blockchain technology. Yeah. Question?
Questions, feedback? I have a question. So looking at the data models, so what type of data would you guys actually collect?
Basically, the core idea was to just one, obviously market data in the regional as in the demand, basically. How many people need meet at any one point, and then the data model would compare that to how much is available in a village, and then find out the right kind of time to actually go to market, because obviously it takes a lot of energy to do something with livestock.
So just to push it a little bit further, how would you actually collect that data?
Oh yeah, that would be by reporting, like having the farmers themselves reporting the stock they have. And obviously market data would be a little bit trickier, obviously, but you could have systems where you create a digital market pricing system, which would be in the interest of the people who trade it as well, I would say. So yeah, it's basically self-reporting. That makes it quite a low-tech solution as well. So you don't actually need all that much infrastructure in order to create it.
Okay. Any other questions, feedback?
Just comment that if you use blockchain, everything will be reflected on your blockchain, so no problem with collecting data. Yeah, it's somehow semi-autonomous.
I mean, yeah. I mean, and then also, self-reporting. We have to kind of understand how we get our data, and sometimes there's going to be gaps in self-reporting.
Sure.
As we saw with the menstrual cycle app. Sometimes when you're feeling great, engage, with the application, but sometimes when things aren't going as well, then, you have
Yeah,
some
we did consider other options, but this was like the most low cost option as possible, because in a village like this, which is that technologically unsavvy, the value to begin with would have to be very small. So you have to start at a very low level.
Right.
That was our reasoning.
And even getting all the resources on blockchain, getting them in a distributed ledger, that takes an effort as
Absolutely,
well.
yeah.
So.
I think if you want to know more about the blockchain, maybe we can talk a little bit about that. I can explain it to you later. Sure. Right now we're limited of time. I think it was 2 minutes.
Yeah.
But thank you for your attention. Yeah. Thank you.
All right. Good job. All right. Next one is education or school.
Oh, great. I'm so sorry. I'm terrible sorry. Take your media. Take carefully. Okay. So, education is important, right? I'm pretty sure that every one of you have ever experienced a plain, boring lecture. Like, totally. So, there is a goal. We want to improve education quality, so we don't have that many Trumps again, right? And, excuse me. One of the reasons why we have actually plain lectures, and very boring ones, is because lecturers don't get feedback, and they keep lecturing, and class after class in school, they don't get feedback, probably they just don't know. So we want to make sure that they get feedback. How do we do that? Well, we want to measure engagement in our students. We want to know, did they like it or not? So we propose a very simple way. Let's say we don't want any sensors. We want the basic minimum of the tools that we're gonna use. So it's just one camera. One camera separates, like it's somewhere there, or it can be a phone camera just placed on a table, so it's very concealed, no one sees that. So, and then we want to collect visual data. We just want to see what everyone is doing during the lecture. And don't be nervous about that, we can just erase the data afterwards. So after we collect the visual data, we run neural network that recognizes spaces in the first place, and then it sees what kind of emotions people have, how long do they actually look at the lecture instead of looking in the phone, right? And to actually get the labels for that data, after the lecture, all we ask our students is from 0 to 10, tell us how likely you will recommend this lecture to a friend, right? So now we know what kind of emotions, what kind of data we can associate with good engagement or like very low level of engagement. So after that, all we do is that we create some kind of a metric, some kind of a rating, and we present the lecture with, okay, this time, this lecture you scored 5, everyone liked it. And he knows that he should continue that lecture in that manner. If he got this very poor score, there is just, for him something to think about. Perhaps the lecture is not that great, or the material is not that interesting. So, and that's how we want to improve the school and education, and by doing this very simple thing. So that's pretty much it. Thank you.
I have a question.
Yeah?
Why do you need two sources of data, visual data and surveys?
So the reason for that, let's say I'm looking at you and I collect your facial expressions, but I don't know what they mean. I don't know what you were thinking. Let's say you were looking at me, probably I'm having something wrong with my attire. I don't know. And at the same time, you're having very boring, like you know that the lecture is very boring, but you're looking at me, but I don't know that. So in order to correctly understand the visual data, we need to know a bit more about
what actual students experience. That's why we need some kind of survey, very simple one, very plain, just from 0 to 10, tell us, how was it? And then after we get this scoring, we can see that, you know, if let's say if most of the time people are looking at the lecture, that means that they're interested. So that's how we can use this to predict next time. Yeah, sure.
I was just because the engagement, there already it's a lot of data on this facial expression on showing engagement, but we don't know. You know, we haven't done. You still have to check with the pupils or the guys that you have there. So you do have to sort of probably get to know. And another thing, you can use this for other things too. You can use it for individual learning. You know, what kind of things engage different types of people. You know, some people like visual, some people like auditory, and so yeah. It can be used for different things later.
The only concern is ethical, I guess.
Yeah, but the thing is, you can after you generate the score, you can instantly remove the visuals, like the clip.
Service,
Yeah.
Yeah, well, one person there.
Yeah, first and foremost, very interesting take on quality of education.
Thank you.
You talk a lot about quantitative data. Have you talked about qualitative data or thought about that in terms of talk about surveys? But have you thought about kind of deepening the feedback from the people sitting in the audience?
Yeah, we discussed that a little bit, but we found out it depends a little bit on the age, and we also know that pupils might not tell the full truth. They are shy. They don't want to tell that I didn't quite understand or I wasn't quite engaged. They want to maybe show their best face to the teacher. So it's that's why we try also to keep it a little bit simple. Would you recommend this to another pupil, for example? So, but yes, ideally that would be good, but it would maybe work better with older
pupils.
Yeah.
I'm thinking also in terms of the reflection of the educator,
Yeah.
so that they kind of get pinpoints of concrete examples.
When it comes to the visual data, people often have different face expressions when they think and focus and are engaged on everything. And while one people are looking at the lecture and actually focusing, another person might be looking at the lecture and having his thoughts drifting away a whole other place. So how do you kind of like make sure that not all the biases in this visual data are just messing it up too much to be able to use it when you do have the survey in addition? Why the visual data?
Well, you can't eliminate bias completely. That's true, and fortunately, this it has to be proven that it works. But the thing is, you always have more than one person in the room. You have more than 5. You can have up to 30, 60 if it's let's say if it's a university especially. So and then there is still a certain type of pattern that on average people have when they're engaged. And even if one individual, he always looks down, I don't know, or his eyes always look down because he has some disability or something. Just because he's one person like that would not influence the data that much. So I guess here would be important to generalize the data and like take the mean. Let's say take the mean time of how long people in general will look at the lecture. So not a single particular people, stuff like that. So it's has to be investigated. I see what you mean.
I think this question can be answered in the opposite way. So if we have, we can train a model on one individual if we have data from different days, and we can learn these individual patterns of behavior, and it wouldn't be a problem at all, right?
Yeah, but then we won't be able to generalize.
The model then, yeah, but that's yeah. If the first model works, that could be an extension, yeah. Yeah. Okay.
Yeah, that's
very
it.
cool. Good job. You guys got me thinking a little bit. The next one, let's end up with transports. All right, so group of transport.
So we went quite a different way from the other group. So we went to the low-tech village, where we started with which form of transport do people use and what do they need. So we went with bicycles because it's easy, cheap, everyone can use it. And well, to start gathering data, we assume a lot of people do have cell phones. So we can use cell phone ping to bases to see general where you're traveling. Are you visiting the town or the village next door, and to get a starting point of the data where people are traveling.
Yeah, so just so the basic needs for transportation is in general like getting water, food maybe. I'm doing my slideshow here. Purposes, work and school. So we're thinking like a rural village, which is not too far from other villages. And as you said, our assumption is they have a mobile phone, smartphone, and roads.
Yeah.
Yeah, for the bicycle. So, what kind of data do we need to collect? At first, before setting up the service, we need to collect historical data, like knowing like the need they have. And for doing that, we will use video. So we will put up a video camera at the ports of entrance in from the village, and use facial recognition so we know like who is leaving and how long are they away. We don't really need to know where they go or for how long. Well, then we will need how long. That's kind of like the historical. But also, well, that's a facial recognition.
As you can see.
As you can see. But also use interviews, like, and ask people about their needs. And while this very nice village bicycle is in operation, we will be able to keep to get data from the bicycle itself. From one thing is the mobile phone of the user, but also GPS on the bicycle.
Yeah, as you can understand when you hear about this, Oslo City has already taken this into their city plan with the Oslo bicycle. Probably familiar with that.
Yep.
So this is the same idea we thought.
Any questions?
Questions, comments?
Yeah, we haven't thought about privacy or anything like that, so that would be a different discussion. Yeah.
We got our lawyers working on that, so.
That's true.
Yes.
Yes.
Now, I'd like to do a compliment. I like your approach on bicycles because pretty much bicycle is one of the main means of transport that is used often in rural areas. So that was smart.
Thanks.
Thank you.
Yeah.
Very good. Good job, you guys. All right, that was wonderful, wonderful. Quite impressed. So how do you guys feel now? Can you take a deep breath? Are you guys ready to go like collect some data and like crunch some numbers and do all those things? You know, it was really brilliant to see how you guys actually formulated the challenges. You know, and as I mentioned, that is such a huge part when you're actually coming up with solutions, is to really identify what challenge you're trying to solve. And that'll help you on the back end, so as you're collecting data, you know exactly what type of data you can actually utilize and what data you may not be able to utilize. All right, so you don't create more work for yourselves in actually coming up with a solution. You know, so how do we collect it? And one group, okay, was actually talking about labeling. Okay, how do we actually label the actual data that we can understand it, but then also a machine can understand it. So they actually have a very defined perspective on what types of data is going in and what is the labels on those particular points of data. And then also scoring, which was also mentioned. All right, so once we actually start running our models, how do we actually score what we're finding? All right, it's quite important because those create averages, they create means, and they also create insights on what we can actually do going forward further. All right, so collecting, labeling, and also being able to score our data is quite important. one of the last things that I wanted to do, are there any other questions while we're going through it? Give you guys yourselves a round of applause. So one of the last things that I can do, if I want to get it to work, I just want to give you guys a little background of what the Weave Foundation actually does. I don't know if this will work, but if it does, then we'll try it. But it's just a short 4-minute video on some of the work that we've been up to. If I can play this. The Weave Foundation was formed in 2010 to source and solve challenges to the world's most pressing problems. We're doing so by bridging the gap between academic knowledge and implementation in energy, education, health, and infrastructure. Our mission is to ultimately bring peace through education. The Weave Foundation's approach is simple. We identify open-ended problems where academic research has developed solutions that are in the process of being applied. The Weave Foundation also leverages local knowledge, capabilities, and technological innovation to devise sustainable solutions specific to local communities. Since its inception, the Foundation has executed projects in the DR Congo, Iraq, Western Sahara, Haiti, and Morocco. One of our longest-standing projects to date is improving malaria treatment production and access in the DR Congo. The program, which began in 2011, helped rural farmers cultivate and transport nearly 56 tons of quinine bark to Pharmakina in the city of Bukavu. The raw material is then processed into life-saving malaria tablets. Our initiative resulted in over 400,000 treatments for malaria and created over 100 new direct or indirect jobs in the farming, pharmaceutical, and transportation industries. In the Middle East, the Weave Foundation is working with youth in politically volatile regions to form solutions for their communities' most dire problems. In July 2015, we implemented an open space technology and design incubator in Iraq. Students completed a community needs assessment to source the challenges facing their community. They conducted 270 interviews and questionnaires with on-the-ground stakeholders and private sector leaders. They later worked to identify and map out solutions to the issues with help from facilitators. We is currently developing the We Solve Labs program in Myanmar to improve the quality of life among vulnerable rural communities, creating new market and empowerment capacities. The activities will follow a 3-pronged process which include skills improvement to increase livelihood opportunities, greater access to social services such as health and education, and participation in an incubator to allow for customized solutions in solar electrification, healthcare, livelihood development, and technology adoption. The Weave Foundation strives to cultivate future leaders and prepare them to utilize their talents in passionate ways. With that goal in mind, we will be launching the We Edge program, a learning model designed for young professionals and innovators to use their talents and skills to make an impact around the world. Through We Edge, developing and empowering new global citizens ready to work on dire global issues. By taking these steps, the World Education Foundation's vision aligns to design and build global learning societies. We believe through education, collaboration, and empathy, the human element is able to generate a quantum shift in consciousness and action, realizing true peace during this generation. The task is tall, and the efforts needed are monumental. Yet through collaborative engagement, activation of lifelong learners, and the ability to connect ideas and people across borders, we are able to architect a system which fosters a cohesiveness between humans, technology, and the environment. Together, we can make a change. Let's create a new world. Thank you guys for participating in this workshop. It's been brilliant, and as you guys continue down the road of exploring data science, yeah, reach out if you feel the need to, and just continue learning. And yeah, we're always here. Thank you.
Do you guys need a short break? Are you feeling good?
Some water.
Water? Yeah? Okay. 5 minutes, and then we'll wrap it up with 2 short presentations, yeah?
spent a couple of days at the campus now, so I thought I'd just give you a short presentation about Noroff, who we are and what we do. We are a private, independent education institution. We got no public funding. It's all privately funded. It's all through student tuition. And we run vocational courses, we run university college courses, and we do almost every single course online. In Norway, for those of you who know the map, we're in Oslo, which is where we're right now, Kristiansand, Stavanger, and Bergen. We're also in the cloud for all our students. All our courses, all our online courses are English. It's modularized. We have 4 startups a year. So in a classroom, you'd start up in August. That's when the academic year starts. We start in January, March, August, and October. And we do part-time and full-time. And all our courses, most of our courses could be, students can top up their vocational education with a 3rd year abroad to do their BA. We got some partners abroad. We got Australia, South Africa, Wales, and England. Information about them there. As a vocational school and as an applied, our university college courses as well. They are research-based, but they're applied. So all the courses are developed in collaboration with the industry. And we like to bring the industry in to help us write the curriculum, write what the students are going to learn. And for our online courses, a lot of it is pre-made. We do a lot of tutorials. We have tutors coming in for the students, and we stream a lot of our lectures out to the online students as well. And we try to bring in industry experts to do that. Our teachers, most of our teachers are actually part-time. They have their business set up outside in the industry, or they work in the industry. They come in and they deliver a module, they deliver their short little thing, or they deliver 4 or 5 weeks, and then they're off again. Or they work half-time here, half-time out. Quickly just run through some of our programs. Some of them are still in development, and some of them are just about ready to be approved. Bachelor of Digital Forensics. That's out there. We've been running it for quite some time now. That's online and in Kristiansand at the University College. And then we got these 2 as vocational programs running here in Oslo. Film and sound. Those of you that have been through the tour have seen the sound studios and the film studio and the equipment, all of that. Then we got our design and media cluster. So graphical design, we got Bachelor of Interactive Media, both animation and design, and animation and games. We got digital marketing, internet marketing as a standalone course. And we got technical design with CAD, which is that makes up the 1st year of our new digital prototyping course, which is going to be launched soon. The 3D cluster, 3D design animation makes up the base for all of it, and then we have games and design, and we're constantly adding on to it. These 2 recently been approved. They're being launched now in August. Front-end development, a 2-year program, and then VFX, visual effects, also a 2-year program. These are the ones in the pipeline. Bachelor of Applied Data Science is actually starting now in August. It's approved, a little bit dated. And digital prototyping, which we're hoping to start in January already, hoping to get it up. Our focus going forward, again, we develop our study programs. We do every single thing we do, we have to do with the industry, and we want to do it with the industry. Develop our staff, continuous development of staff, try to send everyone out on training programs, and also have placements with the industry. So the teachers we do have that is full-time, they work with the industry together to develop the program, so no one gets outdated. That was very short, and that's me. Questions? Any questions?
Where did you get inspiration for opening this this university, this school?
Yeah. Well, I've worked here since 2012. Noroff is about 30 years old. It's actually 30 years old this year. We were located in the city center, so we've only actually been here since August. So when we built the campus, we looked like look towards startup communities, look towards what are they called? English now. Workspaces you can go into and book. We wanted to disconnect the classroom from being locked into one classroom. So here every single student has access to every single room. It's just a matter of doing the competency test and they can go in and access the equipment. We got the computer labs, the Mac labs, all the sound studios, all the film studios, all the common areas. And we're for the students, we're trying to simulate the work life that they're actually going to go out to when they're done. A graphical designer is barely going to work in a team with other graphical designers throughout their career. They're most likely to be working with engineers, to be working with front end and back end developers. They're going to be so that's sort of what we tried to do. Yeah. Okay. Then I'll.
Thank you.
Thank you.
And the round of applause.
So we were going to have a talk on exponential education by Rumman. Unfortunately, she had to leave a little early. So I'm going to go right into the last presentation, which just discusses what our program is for Accel.AI. While I'm pulling that up, I think you guys got a general theme, though, of kind of alternative education models. So obviously Noroff has a similar one from what you guys are traditionally used to here in Oslo, right? Your education system is all pre-set up, as far as I understand, kind of by the government, right? And paid for by the government, is that correct? Yeah? So these alternative education models are becoming very, very popular in other regions. Specifically in the Bay Area, a lot of boot camp programs have also sprung up to solve this problem for technology. And so I'm going to go into this. What is that here?
You might want to try and plug in and plug in.
Oh, let's try that again. Thank you. Are we good?
Yeah.
Pop-up reminding me to play an instrument. Okay, so my name is Laura, and obviously why you're here today, I'm the founder of Accel.AI, and what we are doing is we're lowering the barriers to entry in engineering artificial intelligence while fostering inclusion. So what are the problems we're trying to solve with AI? So one of those problems is scarcity. So we have found that one of the most scarce resources in artificial intelligence today is talent. So we think that, and what we've realized is that most of the time AI engineers and AI researchers come through one specific pipeline, right? Traditional computer science education, but that is not really filling the need of the industry fast enough or well enough, right? So what happens is a lot of these researchers will come through the traditional education program, and they won't have a lot of applied experience, right? They'll have a lot of conceptual and theoretical knowledge, but not a lot of applied experience. So oftentimes these people have to also go through a short training program once they're already in the industry to be able to actually start working at tech companies that they get hired in. So this is a big problem. The other major problem that we're trying to solve is diversity and democratization. So these are two of my favorite people in AI, and both of them also feel very strongly about this issue. So Melinda Gates, one of her most famous quotes is, if we're going to create AI that works for all people, we need a diverse group of people building it, right? So specifically women, people of color, LGBTQ individuals, people or low-income individuals, people that do not normally have access to this space. We want to make sure that they have access to this space. So not only tech, but also artificial intelligence in general. We think if this is going to apply on a larger scale to every industry, that it has to take into account all of those industries together. And then Fei Li is one of the most famous researchers in AI as well, very well known in San Francisco. And really all over the world, I think. She has now developed her own nonprofit for trying to help solve this problem called AI for All. And one of her most famous quotes is, if we do not get more women and people of color at the table, real technologists doing real work, we will create bias systems. And this has been a theme that was going on a little bit in the talks that you've heard so far. Sometimes we have a talk specifically about bias and ethics in artificial intelligence that was not included in this workshop. But this is a real problem that we think needs to be addressed. So how are we solving that problem? We have developed an AI career accelerator. And what that incorporates, first we started out with these workshops. We started in the Bay Area, and now we're also expanding globally. Oslo is our second location. This is our second workshop in Oslo. We're also developing a full career accelerator program, and this is what it will include. So the model we're developing off of is a cognitive apprenticeship model, and that includes milestone projects, a career launch portfolio, hands-on collaboration with your peers, self-paced learning. We want to really help people build an inclusive network. We want to create a holistic environment around learning. And in order to lower those barriers to entry, we offer a pay-as-you-go and also deferment options, as well as scholarships, just like we had scholarships for attending the workshop today. We are a value-driven company, so we really want to focus on innovation and inclusion to drive impact, right? So what this means is not only lowering the barriers for groups that potentially wouldn't have access to the space, but we also want to take into consideration areas in which automation is now going to be reducing the job market, right? So here in Oslo, for example, there's a lot of people that have been working in oil, right? That potentially are going to be replaced by robots. And so, how do we get those people to upskill into another industry, right? And to give them another way to make money and be part of the ecosystem. So these are one of the aspects that we're looking at. You heard a lot of the same thing with, so for example, in agriculture, right? Now robots are going to be moving into doing a lot of farming. So what are we going to do with the farmers, right? Or the trucking industry. Once, self-driving cars are a thing everywhere, right? What are we going to do about all those truck drivers? They're going to need to be reskilled. So again, these are one of the problems that we're trying to solve. So how does Accel.AI solve this problem, and how are we different from what's currently on the market? Well, you obviously are familiar with the traditional degree program. It's usually about a 2 to 4 year program. It's got a very set curriculum. It's very theoretical and research oriented. Usually it costs about $20,000 to $40,000 per year. This is obviously US or San Francisco based amounts. And the average salary for an engineer or researcher in the Bay Area is $76,000 to $160,000. This is just out of graduating. And then we have these coding boot camps that are become very popular in the Bay and also around the US. Usually they're about a 3-month program. They have a very set curriculum, and it's very hands-on and applied learning. So you don't get a lot of theoretical or conceptual aspects, but you do get a lot of that very hands-on experience. Usually costs about $15,000 or $5,000 per month. And the average salary for a junior engineer that comes out of this program is about $58,000 to $78,000 per year. And then there's Accel.AI. And so what we are developing is a subscription-based model that goes up to 7 months for the full program. Our model is evolving with the industry, so we're constantly changing what our curriculum is. It's not set in stone. And so we do that through specific milestones that a student has to reach and learning objectives that they have to meet, right? But it's not specifically set on one area of research or one technology stack, and I'll go more into that in a moment. And we use applied and theoretical learning. So things we talk about also in our curriculum are things like ethics, right? Which is something that isn't normally thought about in coding bootcamp. On top of that, we are charging the industry standard for coding bootcamp, so that's $5,000 per month. Or if you pay up front $28,000 in full for the 7 months. And we expect the average salary for an AI engineer to be about $74,000 to $125,000 that comes out of our program. And these are all average salaries reported by Glassdoor and Course Report online. So what would it look like for someone who's coming through our program with no prior experience? So what we would do is take them through these specific milestones. So if they have no experience in engineering at all, first they would go into Python and computer science fundamentals, right? So they would really have to understand how to work with the language, how to work with algorithms, what data structures are, that kind of thing. We estimate that takes them about 4 weeks. After that, we'll bring them into machine learning fundamentals and deep dives. So really the core aspects of machine learning, a lot of what you guys saw here today, how to start working with data, how to clean data, how to extract it, how to prepare it, and then how to start applying those machine learning algorithms as well. From there, we'll go into big data and deep learning, talking about scale. You know, what would you do if you start potentially get hired at one of those really large tech companies, right? How do you use other more advanced technologies like Spark or Hadoop? How do you start uploading this to the cloud, right? After that, we feel like they have all the skills that they need in order to start working in the industry, right? But they're not quite done with our program yet because we want to make sure that they actually have that hands-on experience. So we do designer and open source projects, right? Once they get the knowledge, they get to apply it. So with these designer projects, we've worked with some tech companies, some accelerators, some startups to really find out what problems people want solved in the industry today. And we're continuing to develop that curriculum as well over time, right? And then open source projects, we want to make sure that when you are applying these learnings to a project in the industry, that they're potentially projects that have a lot of variables, right? So it's one thing if you just create a project really simply, like you saw, for example, Emily's toy project that she came up with for law and politics. That's you know, something that someone would create potentially in a boot camp, right? But wouldn't necessarily have a real-world application, right? So we want to expose them to experiences where they would have a real-world application and would have to potentially consult, you know, with the potential client, right? And go back and forth and see what that process is like. From there, they will also have interview and career coaching. One of the major problems that current boot camps do not address is how someone actually gets a job in the industry once they've gotten all these skills and all this applied knowledge, right? So making sure they're actually prepared in that way and they get that personal development curriculum. And then from there, we're setting up mentorship and internship opportunities for them to go out in the industry and do a specific 3-month internship with our partner programs. So these are some of our strategic partners that we're working with. Obviously, they range from all different areas, but we really want to make sure that we set up the correct partners so that our fellows will be successful in the industry. And obviously, one of our partners here, Noroff, allows us to do these awesome workshops for you guys. So obviously, our plan is to scale globally within the first, so we've actually been only operating for about 10 months. Within the first 6 months, we have hosted workshops in the Bay Area and obviously here in Oslo. We're launching our full flagship program in the Bay Area in September. And then we're going to be launching our second full flagship program here in Oslo as well. And then from there, we're going to other European partners, and then as well as Asia, Africa, India, and so on. So really our moonshot goal is to develop a global network of artificial intelligence engineers, researchers, students, mentors, and consultants on every continent. So that's us. Accel.AI, we are shaping the next generation of AI engineers and enthusiasts. I hope you've enjoyed this workshop, and we'll get to see you again soon. Any questions? No? I guess I did a good job too.
Catch up in time.
Yes. Well, have a good week, everyone. Yeah.
You will send out the link with the Facebook video and all that, or?
Yes. So currently the links are posted on the Facebook event page. Yeah. We're also getting all the slides from all the presenters, and we're going to include that as well on the YouTube page.